Have you ever looked up at the night sky, felt the quiet darkness above you, and wondered, are we alone, or has someone already found us? It's a question that lingers in the human mind, a question as old as our first gaze at the stars. Tonight, or whenever you choose to listen, I invite you to slow down, to breathe, and to allow your imagination to stretch beyond the boundaries of Earth. This is not a hurried lecture, not a rushed documentary filled with loud music and flashing lights. Instead, think of this as a long journey, calm, reflective, and unhurried. A journey where together we will sit back, relax, and drift across the cosmos, exploring mysteries that may hold the answer to one of humanity's greatest questions. Could aliens have already discovered us? The universe is vast, so vast, in fact, that our minds struggle to comprehend its size. Stars upon stars, galaxies upon galaxies, each one containing countless worlds. Somewhere out there, life may have taken root, as it did here on Earth. And if it has, we must ask, have they noticed us? Have distant civilizations turned their instruments toward this small blue planet orbiting an average star and whispered among themselves, "There do you see them?" As you listen, let yourself sink into that thought. What does it make you feel? Curiosity, a sense of wonder, perhaps even unease. There is something haunting about the possibility that we are being watched silently from afar. Yet there is also comfort in imagining that we are not alone, that across the vastness of space, intelligence has blossomed more than once. In this video, we will take our time. Over the next few hours, we'll look closely at the strange visitors that have crossed into our solar system, like the mysterious object known as Oumuamua. We'll talk about another interstellar traveler, 31ATLAS. We'll ask whether such objects could be more than mere rocks or ice. Could they be signs, perhaps even probes, from distant worlds? We'll examine how aliens might detect us, not through spaceships landing in deserts, but through the silent signals Earth has been leaking into space for over a century. And we'll think carefully about what it would mean if they already knew we were here. But before all of that, I want to pause with you. I want you to ask yourself right now, how do you feel about this possibility? When you hear the phrase, aliens might have found us, do you feel excitement, hope, or a tinge of fear? Do you lean forward, eager to know more, or do you step back, cautious of what such an idea might mean for humanity? There is no right or wrong answer. Part of the wonder of this subject is that it invites both awe and caution, both joy and mystery. And as we walk through these questions together, your feelings may shift. You may find yourself more curious, more skeptical, more comforted, or even more unsettled. That is the gift of exploration, discovering not only what lies beyond us, but also what stirs within us. So let us begin this journey with calm hearts and open minds. Picture yourself floating in space, weightless, with Earth far below you. Its blue oceans, green forests, and glowing cities all bundled together on a fragile sphere. Now imagine lifting your gaze outward, past the planets, past the stars, into the vast, dark ocean of the universe. Out there, something may already be looking back. Welcome to this exploration. Welcome to the question, could aliens have already found us? From the moment early humans first lifted their eyes to the night sky, they must have wondered what those shimmering lights were. Were they fires of the gods? Were they other worlds? Or were they simply unreachable mysteries, forever beyond human grasp? That curiosity, the urge to ask what lies beyond, runs like a thread through our entire history. It is not simply a scientific question. It is a deeply human question. Tied to our sense of meaning and place in the cosmos, we search for life because we do not want to believe we are alone. Loneliness, after all, is something every person understands. To imagine that the entire universe, billions of galaxies, trillions of stars, is utterly silent except for us feels almost unbearable. And so we look outward, hoping that somewhere out there, intelligence stirs. and that perhaps we might one day share in a cosmic conversation. This desire is not new. Ancient civilizations recorded myths of beings from the heavens. The Greeks told stories of gods descending from Olympus, and the Mayans tracked the stars with mathematical precision. In each case, human beings tied their destiny to the skies above. They didn't have telescopes or spacecraft, but they had imagination. And imagination was enough to fuel awe. When science began to grow, these questions only deepened. By the 16th century, Copernicus showed that Earth was not the center of the universe, but just another planet orbiting the sun. Later, astronomers like Galileo and Kepler suggested that the stars were not distant lamps, but suns in their own right, suns that might have their own planets. For the first time, it became possible to think not only of life on Earth, but of countless other worlds, each potentially alive. Think about what that realization meant. For centuries, humans had believed themselves to be the focus of creation. Now they began to understand that they were living on a small, fragile rock circling a very ordinary star. In that context, the question, "Are we alone?" became unavoidable. If the universe is so vast, why would life exist only here? Fast forward to the modern era. The 20th century brought new tools: radio telescopes, powerful observatories, and eventually spacecraft. Scientists began to ask the question more directly: if intelligent life exists elsewhere, how could we detect it? The search for extraterrestrial intelligence, or SETI, was born. Instead of waiting for visitors, scientists turned enormous antennas to the sky, listening for whispers across the void. Why radio? Because radio waves can travel great distances with little distortion. In the 1960s, astronomer Frank Drake created an experiment known as Project Ozma, pointing a telescope at nearby stars and listening for signals. He didn't hear aliens, but he proved something important. Humanity was capable of asking the question in a measurable, scientific way. He also developed the Drake equation, a simple formula to estimate how many civilizations might exist in our galaxy. The equation included factors like the number of stars, the likelihood of planets, and the chance of life arising. While each variable was uncertain, the equation forced scientists to confront the scale of possibility. The numbers were staggering, even if the odds of intelligent life were very small. The sheer number of stars, over 100 billion in the Milky Way alone, meant that civilizations could be out there. Many of them might be older, wiser, and more technologically advanced than us. Some might even have noticed us already. But here is where the mystery deepens. If so many civilizations should exist, why haven't we seen them? This is the famous Fermi paradox, named after physicist Enrico Fermi, who once asked during a casual lunch conversation, "Where is everybody?" The paradox suggests that if life is common and if advanced civilizations spread across the galaxy, then surely someone should have visited, contacted us, or at least left behind evidence. Yet the skies remain quiet. The paradox has haunted scientists and dreamers alike. Perhaps civilizations destroy themselves before they can spread. Perhaps they are hiding, deliberately avoiding us. Or perhaps the truth is more sobering. Maybe intelligent life really is extremely rare, and we may be one of the only sparks in this cosmic darkness. Still, the human search continues because not searching feels worse than silence. To look out into the stars is to declare that we are part of something greater, that we are not confined to one small world. The search for life is also the search for ourselves, our identity, our meaning, our place. And so, we listen. Day after day, giant radio dishes sweep across the heavens, waiting for a pattern, a pulse, something that says, "You are not alone." We build telescopes to peer at exoplanets, to analyze their atmospheres for the fingerprints of biology. We send spacecraft to other worlds in our own solar system, drilling into Martian soil and diving through the icy plumes of Enceladus. Searching for hints of life. Every step brings us closer, yet the answer remains just out of reach. It is a question we may not answer in our lifetimes, but it is also a question that keeps us dreaming. As you listen now, I want you to consider, why do you care about this? What stirs inside you when you think of alien life? Do you hope for companionship? Do you fear the unknown? Or do you simply wonder, quietly, if out there, someone else is wondering the same thing about us? This is the beginning of our journey, the search for life, born not only from science, but from longing. Humanity has always looked to the stars. And now, more than ever, we are beginning to understand how to truly listen. If the question, "Are we alone?" has followed humanity since the dawn of time, then the last century has given us something remarkable, the tools to actually search for an answer. For most of human history, the stars were unreachable lights in the sky, far beyond any practical investigation. But today, our instruments can listen across the galaxy, peer into the atmospheres of distant worlds, and even send machines to the icy moons of our solar system. Each tool is like a new sense, extending human perception into realms once thought impossible. One of the most iconic tools in this search is the radio telescope. Unlike optical telescopes, which gather light, radio telescopes capture invisible radio waves that flow through the universe. These signals are powerful because they travel vast distances, relatively undisturbed, slipping past dust clouds that block visible light. When humans began transmitting radio in the early 20th century, we unknowingly announced ourselves to the cosmos. Our earliest broadcast, simple Morse code, military communications. Even early television shows are now rushing outward at the speed of light, forming a growing bubble of human presence. This bubble is only about 100 light-years wide. On the cosmic scale, that's barely a drop. But within that sphere lie thousands of stars, each with the potential to host planets. If intelligent civilizations exist in that region, they might already know about us, faintly catching the echoes of our presence. And if we can imagine them listening, it makes sense for us to do the same. That is the essence of SETI, not just sending, but listening. Radio telescopes like the giant dish at Arecibo, before its collapse and the enormous arrays scattered across deserts, have spent decades listening for signals that stand out from the background noise of the universe. Most of the time, they detect natural phenomena, pulsars, quasars, the steady hum of cosmic radiation. Yet the search persists because even one artificial signal, even a simple repeated pattern that nature could not produce, would be enough to prove we are not alone. But our search doesn't stop with radio waves. The modern age of astronomy has given us another extraordinary gift: the ability to detect exoplanets, worlds orbiting stars beyond our sun. 30 years ago, no one knew for certain if planets existed outside our solar system. Today, thanks to missions like Kepler and TESS, we know of thousands. These discoveries have transformed our perspective. The galaxy is not just filled with stars, it is filled with planets, many of them potentially Earth-like. Detecting them is no small feat. Planets are tiny compared to their stars, and far too faint to see directly in most cases. Instead, astronomers use clever techniques. One method, the transit method, watches for the tiny dip in starlight when a planet passes in front of its star. Another, the radial velocity method, looks for the wobble in a star's motion caused by the gravitational tug of an orbiting planet. Together, these techniques have painted a picture of a galaxy rich with diversity. Gas giants larger than Jupiter, rocky super-Earths, and worlds orbiting in the habitable zone where liquid water might exist. But finding planets is just the beginning. The next step is to analyze their atmospheres, searching for signs of life. Certain gases, oxygen, methane, water vapor, could act as biosignatures, chemical evidence of biological processes. With the James Webb Space Telescope and future missions like LAVOR or HABEX, We are on the cusp of being able to study alien skies in detail. Imagine the impact if we were to find oxygen-rich air on a distant planet. It would not prove intelligence, but it would strongly suggest biology. A living world, breathing beneath another sun. Closer to home, our search also extends across our own solar system. Mars, with its ancient riverbeds and seasonal methane plumes, remains a tantalizing candidate. Robotic explorers like Curiosity and Perseverance dig into the red soil, searching for organic molecules and signs of ancient microbes. Beyond Mars, icy moons like Europa and Enceladus excite scientists even more. Beneath their frozen shells lie oceans of liquid water, warmed by tidal forces from their parent planets. These hidden seas could be cradles for alien microbes, and perhaps even more complex life to reach them. We build spacecraft equipped with instruments more delicate than any human hand could craft. Some probe icy geysers, capturing frozen particles to analyze. Others map surfaces in detail, searching for weak points where future missions might dive. Each spacecraft is not just a machine, it is an extension of human curiosity, a physical embodiment of our longing to know. But perhaps the most daring tool of all is one we built to send a message outward. In 1977, the Voyager spacecraft left Earth carrying the golden record, a phonograph disc with sounds and images of humanity, greetings in dozens of languages, music from across cultures, and even diagrams of our solar system. It was a time capsule, a message in a cosmic bottle. The Voyagers are now billions of miles away, in interstellar space, silently drifting. If anyone finds them in the distant future, they will know that humans once looked up and cared enough to introduce themselves. What's striking about these tools, radio telescopes, exoplanet hunters, planetary probes, is that they represent a shift in how humanity sees itself. For thousands of years, the stars were unreachable. Now, with antennas and lenses, with rockets and records, we are slowly learning how to stretch our senses into the void. Still, there's a humility to all of this. Our instruments are powerful, but the universe is unimaginably vast. Even the best telescopes can only glimpse tiny corners of the sky. Even our strongest signals fade into background noise after a few hundred light years. It may be that civilizations exist but are simply beyond our reach. Their signals too weak, too far, or too different for us to recognize. Yet we keep searching. Not because we are certain we will succeed, but because searching itself is a declaration. It is a way of saying, we are here, we care, and we are willing to listen. Every antenna built, every telescope launched, is a monument to human hope. And even if the universe remains silent, the act of reaching outward changes us. It reminds us that we are part of something larger, that we live not on an isolated island, but within a vast and mysterious sea. As you think about these tools, consider what they represent. They are not just machines. They are extensions of our senses, our voices, and our dreams. They are humanity's way of asking the universe a question and waiting patiently for an answer. When we ask, are we alone? We are not only asking about aliens. We are, in a sense, asking about ourselves. The search for life is as much a mirror as it is a telescope, reflecting our own hopes, fears, and values back at us. It's not just about what we might find out there. It's about what we learn about humanity in the process. At its core, the meaning of the search is tied to identity. For centuries, human beings placed themselves at the center of existence. Earth was the hub of creation and everything else revolved around it. Science eventually showed otherwise. We are orbiting a star, drifting in a galaxy among billions, surrounded by a universe that dwarfs us. Each discovery has humbled us, shifting our sense of importance. To ask whether life exists elsewhere is to continue that process. If we are not alone, then we are not the pinnacle of creation. We are participants in a far larger drama, for many. This is a comforting idea. The universe, vast and often empty, feels less lonely if we imagine others looking back at us. It means that intelligence is not unique to Earth, that our existence is not a rare accident. It suggests that consciousness, creativity, and culture might be woven into the very fabric of the cosmos, appearing wherever conditions allow. The stars, then, are not just distant lights, they are potential homes, each with stories of their own. But for others, the idea sparks unease. If aliens exist, what would they think of us? Would they see us as equals or as primitives? Would they come in peace or with intentions we cannot even begin to predict? The history of human contact between different cultures is filled with stories of conquest and exploitation. Perhaps advanced civilizations might be kind to roar, perhaps not. This tension between hope and fear is part of what makes the search so powerful. It forces us to confront both our optimism and our caution. Beyond personal feelings, the search also carries cultural weight. When we listen for alien signals, when we send probes into space, we are creating a legacy. Future generations may one day look back at these efforts as the moment humanity first reached beyond itself. The golden record, drifting with Voyager, is not only a message to the stars, it is a message to our descendants. Proof that we cared enough to try. Think about what that says about us. We are a species struggling with countless problems: wars, poverty, inequality, climate change. And yet, even in the midst of all this, we still find time to ask questions about the stars. That persistence is a testament to something uniquely human: the refusal to let daily survival be our only concern. We dream even when dreaming seems impractical in this sense. The search for life is not separate from our struggles on Earth, it is connected. To search the cosmos is to practice humility, patience, and cooperation. Projects like SETI or the James Webb Space Telescope require international collaboration, resources pooled from across nations. The act of looking outward unites us, if only briefly, under a shared curiosity. It reminds us that whatever divides us here, we all live on the same fragile planet, under the same sky. There is also a deeper layer to the meaning. Some thinkers argue that the search is not only about finding aliens, but about defining what it means to be human. Imagine the moment we detect an unmistakable signal, a structured artificial broadcast from another star. The content of that message may matter less than the realization itself. In that instant, we would know: intelligence is not unique. Consciousness has arisen more than once. The human story would no longer be the only story. That realization would ripple through every field: science, philosophy, religion, art. Entire belief systems might be challenged. Some would celebrate, seeing it as proof of a greater cosmic order. Others might struggle, feeling diminished or threatened. But one thing is certain: humanity would never see itself the same way again. Even the possibility of that moment changes us in advance. By preparing for it, by building telescopes and writing equations, we stretch our imagination. We become a species that does not merely look inward, but outward. We become a species willing to accept that we are part of something larger, even if we don't yet know what that something is. And here lies perhaps the deepest meaning of all. The search is a form of hope. Hope that the universe is not indifferent. Hope that across the dark gulf of space there are minds capable of understanding us. Hope that we might one day bridge the silence with connection. Even if the search takes centuries, even if no signal ever comes. The act itself says something profound. We believe it is worth asking. As you reflect on this, I encourage you to pause and think. What would it mean to you if aliens existed? Would it comfort you, frighten you, inspire you? Would you feel smaller, or would you feel connected to something greater? There is no single answer, only the richness of possibility, and so the human search for life continues, driven not only by science, but by longing, imagination, and a refusal to stop asking. Every telescope we build, every probe we send, every signal we listen for, is part of this unfolding story. Whether or not we ever find aliens, the journey itself has meaning. It teaches us humility. It sparks our creativity. It binds us together under the stars. This is why the search matters. It is not just about them, it is about us. About who we are, what we value, and how we choose to live in a universe that may be far less lonely than we once imagined. In October 2017, astronomers observed something extraordinary, an object unlike any they had ever seen before. It was swiftly moving through our solar system, following a trajectory that made it clear it did not originate here. This was not a comet from the outer reaches of the Kuiper Belt, nor an asteroid slowly drifting from the inner solar system. It was something else entirely, an interstellar visitor. The object was named Oumuamua, a Hawaiian word meaning scout or messenger, fitting for something that had traveled across the vast distances of space, passing through our cosmic neighborhood and then disappearing as quickly as it had arrived. What made Oumuamua so remarkable? For one, its trajectory and speed indicated it had come from beyond our solar system. No gravitational interactions could explain its motion entirely. It was moving too fast, and its path curved in ways that suggested an origin from a distant star system. This alone would have been enough to fascinate astronomers. But the object's physical characteristics added another layer of mystery. First, its shape. Observations suggested that Oumuamua was long and thin, perhaps hundreds of meters in length, but far narrower in width, almost cigar-shaped. This form is unusual compared to comets or asteroids we see within our solar system. Most natural objects tend to be more spherical or irregular, but this elongated figure seemed almost unnatural, twisting and tumbling as it sped through space. Then there was its brightness. As it tumbled, the light reflecting from its surface varied dramatically. This suggested that it was rotating in a chaotic manner, not a steady spin like most asteroids. Scientists quickly realized that such tumbling could tell us something about its internal structure. Perhaps it was solid and dense, resistant to breaking apart even under the stresses of interstellar travel. Or perhaps it was unusually rigid, a survivor from an extreme environment far beyond our sun. But the most intriguing feature, the one that sparked global debate, was the small acceleration Oumuamua experienced as it left the solar system. It did not simply follow a path dictated by gravity alone. Something was pushing it slightly off course. Could it be outgassing like a comet releasing vapor as it neared the sun? Surprisingly, telescopes saw no evidence of a comet-like tail. No visible jets of gas or dust. This puzzle led some researchers to consider extraordinary possibilities. Harvard astronomer Avi Loeb proposed a bold hypothesis. Could Oumuamua be an artificial object, a probe sent by an alien civilization? He suggested that its unusual shape and unexpected acceleration could be explained if it were a thin, lightweight structure, solar sail, perhaps, pushed by radiation from the sun, while many in the scientific community remained skeptical. The very fact that such a hypothesis could be discussed openly highlights just how mysterious this visitor was. Others offered more conventional explanations, though none were entirely satisfying. Some theorized that Oumuamua might be a fragment of a larger object, torn apart in another system and flung into interstellar space. Some suggested it was a chunk of frozen nitrogen or even a piece of hydrogen ice. Though these scenarios raise their own problems, how could such fragile material survive the journey across light years without evaporating? Despite all the theories, one thing is clear: Oumuamua defies easy classification. It arrived unexpectedly, passed through our solar system in a matter of weeks, and then vanished into the darkness, leaving behind only questions. Its brief visit was a reminder of how little we know about the cosmos. and how much may be passing by unseen, silently. In the vast emptiness between stars, the arrival of Oumuamua also changed how astronomers think about interstellar objects. Before its discovery, we had no confirmed examples of objects entering our solar system from beyond. The sheer rarity made it a historic event, cosmic first. Scientists immediately began reevaluating models of planetary formation and the likelihood of material traveling between star systems. Could objects like Oumuamua be more common than we think? Simply difficult to detect because they move so fast and are so small. For the public, Oumuamua ignited the imagination. News outlets around the world speculated wildly. Was it a spaceship? A probe? A message from the stars? While most of these ideas are speculative, they highlight the enduring fascination humans have with the unknown. Even a small, tumbling rock can capture our attention if it hints at the possibility that we are not alone, as we consider Oumuamua. It is important to remember the scale of what we are dealing with. This object traveled for millions of years, crossing the void between stars, and passed within a fraction of a distance from our sun, a cosmic coincidence that allowed us to glimpse it at all. How many other travelers have come and gone, silently, unnoticed? Could they carry information, or perhaps even microbes, from distant worlds? The questions multiply, and with each one, our curiosity deepens. In the end, Oumuamua is a symbol of the universe's mystery. It reminds us that space is not empty, and that sometimes the extraordinary arrives without warning. Whether natural or artificial, it challenges our understanding and invites us to look beyond, to consider the possibility that the cosmos is alive with stories we have yet to discover. And perhaps, somewhere among those stars, civilizations are also looking outward, asking their own questions. Who else is out there? Just 2 years after Oumuamua's brief, enigmatic journey through our solar system, another interstellar visitor was detected, confirming that such cosmic travelers are not unique events. This new object, designated 3I-ATLAs, or sometimes referred to simply as C2019 Q4, was discovered in late 2019 by the asteroid Terrestrial Impact, Last Alert System Atlas, for which it is partially named. Like Oumuamua, it came from far beyond our solar system, entering on a hyperbolic trajectory that marked it as a true interstellar object. 3I Atlas immediately caught astronomers' attention for several reasons. First, it approached from a completely different direction than Oumuamua, suggesting that the influx of interstellar objects might be more common than previously assumed. Its velocity was consistent with an origin outside our stellar neighborhood, confirming that the Sun is not isolated. It is just one star among billions, passing through a galaxy filled with wandering debris from other systems. Physically, 3I resembled what astronomers expect from a conventional comet. Unlike Oumuamua, it displayed a faint but clear coma cloud of gas and dust surrounding its nucleus, evidence of outgassing as it neared the Sun. This cometary activity made it easier to study compared to the enigmatic Oumuamua, which seemed devoid of typical cometary features. Still, the fact that it traveled from another star system made it an object of profound interest. It was literally a messenger from elsewhere, carrying material that had been shaped in another planetary environment. Spectroscopic analysis of 3I-ATLAS's coma revealed compositions similar to what we see in long-period comets from our own solar system. Water vapor, carbon-based compounds, and dust particles all hinted at a familiar chemistry. Yet the object's history was radically different. It had likely traveled for millions of years through interstellar space, enduring cosmic radiation, collisions with microscopic particles, and the chill of near-absolute zero temperatures. Its survival alone was remarkable. The discovery of 3I Atlas had another effect. It forced scientists to rethink the likelihood of interstellar objects entering our solar system. Before Oumuamua, Interstellar arrivals were considered exceedingly rare, almost one-in-lifetime events. But within just a few years, 2 objects had been observed. This suggested that countless others may pass through our neighborhood unseen. Too faint or too fast for our current instruments to detect. The galaxy, it seemed, is far more interconnected than previously imagined. The similarities between Oumuamua and 3I Atlas naturally sparked speculation. If one interstellar object had entered our solar system, and now a second, could some of them carry more than dust and rock? Could they be probes deliberately sent to investigate distant systems? The idea remains speculative, yet it is taken seriously enough by some scientists to merit discussion. After all, the universe is unimaginably old, and any civilization advanced enough to send spacecraft across light years could have mastered methods to survive the journey. Perhaps sending automated scouts to observe other worlds in popular imagination. 3-1 ATLAs reignited the debate ignited by Oumuamua. Headlines speculated about alien probes, messages in transit, and the possibility that these visitors were signs of intelligence reaching out to us. While most scientists caution that natural explanations are overwhelmingly more likely, the very fact that these objects arrive at all challenges our assumptions about the solar system's isolation. Each new visitor serves as a reminder that the Sun's neighborhood is not a vacuum. It is a highway for objects wandering the Milky Way. It's carrying secrets from its home system. 3I Atlas also offered an unprecedented opportunity to study material from beyond the solar system directly. While we cannot capture the object, and it will soon continue its journey out into interstellar space, every observation we make provides a snapshot of what planets and comets in other systems are like. Scientists can analyze isotopic ratios, chemical signatures, and dust properties, giving indirect insight into planetary formation elsewhere. In this sense, these objects are natural. Probes delivering samples of alien systems without requiring a spacecraft mission. The objects fleeting. Visit also reinforces the challenge of detecting extraterrestrial artifacts. If a civilization had sent probes deliberately to observe Earth or other nearby systems, they might look like 3I Atlas or Oumuamua, small, fast, and nearly invisible to the naked eye. Our current technology allows us to see only the largest or closest interstellar arrivals. There could be countless other objects passing through silently, unnoticed, each a possible messenger of another world. As we consider 3I Atlas, it is worth pausing to reflect on what these discoveries mean for the broader question of alien detection. The universe is vast, and direct contact spaceships landing, signals arriving, is likely extremely rare. Yet objects like 3I Atlas demonstrate that indirect encounters are possible. Even a silent rock, drifting from another star, may carry clues about life elsewhere, or at least about the processes that shape planetary systems. It is a subtle, almost poetic form of contact, the cosmos reminding us that we are not alone, even if it does so in whispers rather than shouts in the end. 3-1 Atlas and Oumuamua are more than scientific curiosities. They are symbols of a universe alive with motion, a cosmos that does not confine itself to our expectations. They challenge us to think beyond the familiar, to accept that visitors from the stars may be passing through unseen every day. And they remind us of the fundamental lesson of astronomy, that space is not empty, and that sometimes the most ordinary-looking objects may carry extraordinary stories as you listen. Allow yourself to imagine these travelers silently moving through our solar system, carrying fragments of alien worlds, perhaps even the faintest echoes of distant civilizations. What might they see if they could observe us? And what might we learn if we could only follow them on their journey back to the stars? While Oumuamua and 3I Atlas have captured the imagination of astronomers and the public alike, they also open a much larger question. How often does material from other star systems actually visit ours? And by extension, could intelligent civilizations have ever found us or even be observing us now? The truth is, the galaxy is full of wandering debris. Stars form in clusters, and during those early periods of planetary system formation, gravitational interactions can eject asteroids, comets, and dust into interstellar space. Over millions or billions of years, these objects drift, sometimes passing through distant star systems, occasionally intersecting with planets like Earth, while most of these travelers are microscopic or too small to detect. Occasional larger objects, like the ones we've seen, make a brief and spectacular appearance. Scientists have long theorized about the frequency of such events. Studies suggest that our solar system might be visited by small interstellar objects every year or so, though most are simply too faint and fast to detect with current telescopes. In other words, Oumuamua and 3I ATLAS might be only the tip of the iceberg, a glimpse of a constant cosmic traffic flowing through our neighborhood. If true, these interstellar objects are not anomalies, but part of a vast galactic ecosystem, silently exchanging material between star systems. But interstellar visitors are not limited to rocks and dust. The more speculative and thrilling possibility is that intelligent life elsewhere could send probes to observe other worlds, including ours. While there is no confirmed evidence of such probes, some researchers have argued that small, fast-moving objects like Oumuamua could serve as natural disguises for observational devices. Imagine a civilization capable of constructing durable, lightweight probes designed to survive interstellar travel. They could blend in with ordinary interstellar debris, passing through planetary systems without detection. This possibility raises another question. Could extraterrestrial civilizations have detected us already? Our planet has been broadcasting electromagnetic signals for over a century. Radio waves, television transmissions, and radar signals have been radiating outward, forming a sphere of influence roughly 100 light-years in radius. Any civilization with sufficiently sensitive instruments could, in theory, intercept these signals and recognize them as evidence of intelligent life. But the universe is vast, and the signals weaken with distance. Detecting them requires technology far beyond our current capabilities. There are also practical challenges for alien visitors. Traveling across light years is no small feat, even at near-light speeds. Journeys to even the nearest stars take years or decades. A civilization capable of sending probes must have overcome immense engineering, energy, and logistical hurdles. Yet the same could be said about us if we ever attempt interstellar travel. Perhaps the rarity of such civilizations makes encounters like Oumuamua and 3I Atlas especially precious. They remind us that interstellar travel is possible in principle, even if it is staggeringly difficult in practice, beyond speculation. Scientists have considered indirect ways to determine whether Earth has been visited in the past. Meteoritic studies, for instance, can reveal material that originated beyond our solar system. Tiny interstellar dust particles have been collected in the Earth's atmosphere and in samples returned by missions like Stardust. These grains can carry isotopic fingerprints, indicating that they formed around other stars billions of years ago. While these particles are microscopic, they provide a tangible connection to other systems. A reminder that our solar system is not closed off. Astronomers have also studied anomalies in the solar system that could suggest past interstellar influence. Some objects in the outer solar system with unusual orbits or chemical compositions may have originated elsewhere or been perturbed by unknown forces, while nothing conclusively points to intelligent visitors. The fact that so many interstellar objects are now being discovered suggests that the boundary between star systems is porous and active, rather than isolated and static. From a philosophical perspective, this opens a fascinating dimension of possibility. The universe could be teeming with observers, but we simply lack the ability to detect them. They could be watching silently, their methods invisible to us, or they could have passed long before humanity emerged. The scale of time and space is so vast that what seems improbable to us may, in cosmic terms, happen regularly. Yet how would we know if a civilization had visited or detected Earth? There are a few theoretical signs. Unexplained technological anomalies. Objects behaving in ways that defy natural physics could hint at artificial origin. Signals with non-random patterns. Unlike natural radio waves, a deliberate broadcast might have structure, repetition, or encoded information. Physical artifacts. An interstellar probe or object left in orbit around the Sun or a planet could be detected by telescopes, although this would require extreme vigilance. So far, no such definitive evidence exists. Every mysterious object or signal discovered has had a plausible natural explanation, from cometary activity to instrumental artifacts. Yet the absence of proof is not proof of absence. The universe is enormous, and we have observed only a tiny fraction of it. The sheer possibility of being observed or of observers passing silently through remains open. The implications of these considerations are profound. If we are visited or observed, it might not come in the dramatic fashion often depicted in fiction. Instead, it could be subtle, almost imperceptible, like a small rock tumbling past the Sun, carrying with it the distant signature of another system. These encounters may already be happening, unnoticed, while we continue to look outward through our telescopes, eager to find something extraordinary ultimately. The question of whether other systems have visited Door, whether aliens know about Usenvite's reflection. It reminds us of the fragility and uniqueness of life on Earth, but also of our connectedness to the wider galaxy. Interstellar visitors, whether natural or artificial, reinforce that the universe is dynamic, filled with motion, exchange, and potential contact. They are messengers in the truest sense, reminders that humanity exists in a larger cosmic context, a participant in a universe far grander than we can fully grasp as you imagine these possibilities. Consider this: every interstellar object, every signal, every particle that drifts between stars is a potential bridge to the unknown. We may not yet have definitive proof of alien intelligence, but the universe is generous with hints. It challenges us to observe carefully, to question deeply, and to remain open to the extraordinary. And perhaps, just perhaps, one day a visitor from the stars will pause long enough for us to notice, and the question of whether we are alone will finally have an answer. For billions of years, Earth has quietly orbited the Sun, a small blue planet teeming with life, yet almost invisible against the vast darkness of space. But in the last century, humanity has begun to leave a mark, signals that reach beyond our atmosphere and into the cosmic void. If an alien civilization were searching for signs of life, how would they detect us? Could they even notice the signals of our existence among the billions of stars? One of the most obvious signs is our electromagnetic emissions. Since the early 20th century, radio waves, television broadcasts, and radar signals have been radiating outward at the speed of light. These waves form an expanding sphere around Earth, now roughly 100 light-years in radius. Any civilization within that range, equipped with sensitive enough instruments, could detect our presence. Our TV signals, for example, carry patterns and structures distinguishable from natural sources, revealing both energy use and technology. But detecting these signals is not straightforward. Electromagnetic waves weaken with distance, spreading thinner as they travel. By the time our early broadcasts have crossed even a few dozen light-years, they're faint, easily drowned out by the background noise of space. An advanced alien civilization would need large, sensitive arrays, perhaps similar to or more powerful than our own radio telescopes, to pick up the faint whisper of human activity beyond electromagnetic signals. There are other signs that we have left behind. Spacecraft and satellites are increasingly populating near-Earth orbit. Thousands of artificial objects circled the planet, From the International Space Station to communication satellites and remnants of defunct satellites. These objects reflect sunlight and emit signals of their own, making Earth's neighborhood unusually bright and complex compared to most planets in our galaxy. Even our own atmosphere carries clues. Industrial activity has altered the chemical composition of our air. Nitrogen oxides, methane, carbon dioxide, and other trace gases create a distinctive signature that might be detected spectroscopically from afar. If an alien civilization scanned our planet's atmosphere with the right instruments, they could infer not only the presence of life but also technological activity, technosignature, indicating intelligent species. Then there are the long-term artifacts. Human-made debris is spreading into space at an accelerating pace. The Voyager probes, launched in the 1970s, carry the Golden Record, a symbolic message designed to introduce humanity to other civilizations. Though it is unlikely that Voyager will ever be intercepted, it represents the deliberate act of signaling our existence. Every probe, every object leaving Earth's gravity, increases the chances that something, somewhere, might notice our presence. But how obvious are these signs to a distant observer? Could they realistically pinpoint Earth as an inhabited world? Some astronomers argue that while the signals are detectable, only a civilization intentionally searching for Earth would find them. The electromagnetic sphere is tiny on a galactic scale. Moreover, only civilizations within a few dozen to 100 light-years could currently intercept our early broadcasts. Beyond that, our presence might remain invisible, and we would appear as just another quiet, unremarkable planet orbiting an ordinary star. This leads to a subtle but important point. Visibility depends on both capability and intent. An advanced civilization with sufficient technology may be able to detect faint signs of our planet, but they must also be looking in the right direction at the right time. Unlike humans searching for distant stars, which requires planning, observation, and interpretation, the detection of Earth is contingent on alignment between observer and observed. In other words, just because we emit signals doesn't guarantee anyone is listening. There is also the question of interpretation. Even if aliens detected our radio emissions or chemical signatures, would they recognize them as evidence of intelligent life? Perhaps they would perceive them as unusual natural phenomena. Or perhaps they would understand the patterns as deliberate signals. This uncertainty underscores the challenge of cosmic observation. Detection does not automatically imply comprehension. Interestingly, some scientists consider the possibility of accidental artifacts in the form of space debris or long-range probes. Interstellar objects like Oumuamua or 3I Atlas could, in theory, act as passive carriers of information about their origin. If an alien civilization were sophisticated enough to examine these objects, they might detect isotopic signatures, chemical compositions, or physical structures hinting at a planetary system capable of supporting life. In a sense, we may already be sending information about Earth and its biology into space. Not deliberately, but simply by existing and interacting with the cosmos. Finally, there is the philosophical angle. The mere fact that we are asking these questions indicates something profound about humanity. We are aware of our potential visibility. We are curious about our place in the universe. We are simultaneously the observed and the observers capable of reflecting on the possibility that other eyes may be watching. This self-awareness is a technosignature in itself, reminder that life capable of contemplation and inquiry has emerged on this small blue planet as we think about the signs we leave behind. It's worth imagining the perspective of an alien civilization. What would they notice first? Our atmospheric alterations. Our satellites reflecting sunlight. Our radio transmissions pulsing faintly through the void. Or would they pass by Earth, seeing nothing out of the ordinary? A single planet among billions, waiting for a civilization to grow more conspicuous over millennia. Whatever the case, the question of whether we have been noticed remains open. The universe is vast, the timescales immense, and the possibilities almost infinite. Yet every signal we send, every object we launch, every alteration we make to our world, adds to the likelihood that someday someone might take note. And in considering that, we gain not only knowledge about the cosmos, but also insight into ourselves, our curiosity, our ingenuity, and our profound desire to connect beyond our tiny, fragile world. If we imagine ourselves as part of a galactic conversation, the question naturally arises: could extraterrestrial civilizations detect us, and could we detect them? This is the essence of the search for intelligent life beyond Earth, in the same way that we listen for signals from distant stars. It is plausible that other civilizations are observing, attempting to understand the cosmos, and perhaps even searching for signs of life on planets like ours. The first place to consider is the electromagnetic spectrum. Just as humans emit radio waves, television signals, and radar, a technologically advanced civilization might broadcast signals for communication, navigation, or research purposes. These emissions, if strong enough and targeted correctly, could traverse light years, potentially reaching distant star systems. An alien civilization could, in principle, detect unusual patterns, repetitive pulses, or structured signals that stand out from the cosmic background. For decades, SETI, the search for extraterrestrial intelligence, has focused on detecting such signals. By scanning the skies with radio telescopes tuned to quiet frequencies, scientists hope to identify patterns that cannot be attributed to natural phenomena. The detection of a narrowband repeating signal would be a strong indicator of artificial origin. Just as Morse code conveys information across vast distances, extraterrestrial signals could be deciphered if they contain repetition, mathematical patterns, or encoded data. But detecting alien signals is not simple. The vastness of space dilutes and disperses energy over distance, making faint transmissions difficult to distinguish from noise. Furthermore, intelligent civilizations might use forms of communication beyond our current understanding, such as lasers, neutrino beams, or gravitational waves. These modes could be invisible to our instruments, leaving us blind to their presence. In other words, even if signals are being sent, we may lack the technology to receive or interpret them. Interestingly, some scientists consider the possibility that interstellar objects themselves could serve as carriers of information. Just as we speculated that Oumuamua might be an artificial probe, it is conceivable that other civilizations could dispatch durable objects carrying data or instruments designed to observe other planetary systems. These probes could remain dormant, traveling across light years until they reach a target system. Observing such objects requires careful attention to their trajectories, unusual motion, or unexpected properties, and even then, distinguishing them from natural debris is a monumental challenge. There are also passive signals to consider. A civilization might not deliberately broadcast messages, but could be detectable through its industrial activity or planetary modifications. The concept of technosignatures encompasses all such evidence: atmospheric pollutants, large-scale energy usage, orbital structures, or even artificial illumination visible from space. For example, a planet with large swaths of light reflecting cities, or distinctive chemical patterns in its atmosphere could reveal the presence of technology. In this way, observation does not require active communication. It only requires sufficiently sophisticated detection techniques. The difficulty is compounded by the timescales involved. Even if a signal from an alien civilization were traveling toward Earth, it might have been sent hundreds or thousands of years ago. Similarly, our own signals may take centuries to reach their intended recipients. This creates a scenario where civilizations could exist in isolation from each other, their broadcasts crossing paths only after long, silent intervals. In this cosmic sense, The chances of two civilizations actively engaging in real-time conversation are extraordinarily slim. Yet, the very search for signals encourages us to improve our detection capabilities. Modern radio telescopes, like the Allen Telescope Array, are scanning millions of frequencies, monitoring for structured emissions. Optical SETI programs search for laser pulses that could carry information across interstellar distances. Future technologies may extend our reach further, enhancing our ability to detect subtle patterns that might otherwise be invisible. Another intriguing consideration is the possibility of deliberate messages directed at Earth. Some theorists propose that an advanced civilization might intentionally aim probes or signals toward planets showing signs of life. Oumuamua and 3I Atlas, though most likely natural, raise the hypothetical scenario of objects sent with observational intent. If so, Earth could already be under passive observation, our signals being recorded and analyzed without our knowledge. The universe, in this vision, is not silent. It is quietly listening. Beyond purely technical detection, there is the philosophical question of interpretation. Suppose we do detect an anomalous signal, how would we know it is alien in origin? Scientists rely on several criteria: non-random structure, repetition, and patterns consistent with information encoding, signals exhibiting mathematical constants, prime numbers, or structured sequences are unlikely to occur naturally and could indicate intelligent origin. However, even with these clues, interpretation remains challenging. We must differentiate between natural astrophysical phenomena and potential messages from an intelligent source. Finally, the search for alien signals encourages us to reflect on our own activities. As we send spacecraft into interstellar space and expand our technological footprint, we become part of the cosmic conversation. Every transmission we send, every probe we launch increases the chance that another civilization could detect us. In the future, humanity itself may deliberately broadcast messages, aiming to announce our presence or establish contact. These actions, while speculative, underscore the interconnectedness of observation and communication in the galaxy. In summary, the detection of alien signals involves a delicate balance of technology, intent, and interpretation. We may already be receiving whispers from distant civilizations, or perhaps the universe is silent in our local region. Regardless, the pursuit of these signals reveals much about our own curiosity, ingenuity, and the profound desire to connect beyond the bounds of Earth. Every scan, every listening session, is a small but meaningful step toward understanding whether we are truly alone, whether other eyes are observing us across the cosmic ocean. Imagine for a moment that a distant civilization has detected our presence. Perhaps they intercepted our electromagnetic signals, observed the chemical signatures of our atmosphere, or even noticed our technological artifacts drifting through space. What would this mean, not only scientifically, but for humanity itself? The implications of being found are as profound as they are complex, spanning technological, philosophical, and existential dimensions. From a scientific standpoint, the discovery that we have been observed by intelligent beings would revolutionize our understanding of life in the universe. Until that moment, we have speculated, theorized, and searched, yet had no concrete evidence of extraterrestrial intelligence. Confirmation that another civilization exists would transform fields ranging from astronomy and biology to engineering and philosophy. It would validate our understanding of the rarity or ubiquity of life and demonstrate that intelligence is not confined to Earth, yet the consequences extend beyond science. The knowledge that another civilization is aware of us could reshape our perception of ourselves. Humanity has long considered itself the sole observer of the cosmos, capable of reasoning, curiosity, and creativity. Suddenly, we would realize that we are being watched, that our achievements and failures exist in a broader cosmic context. This awareness could foster humility, encouraging a deeper appreciation for the fragility and uniqueness of life on Earth. However, implications are not uniformly reassuring. The unknown nature of these observers invites uncertainty, even fear. Are they benevolent, indifferent, or hostile? Our history shows that encounters between civilizations at different technological levels often result in disruption or conflict. Extrapolated to an interstellar scale, such encounters could carry enormous consequences. While speculation abounds, the mere possibility of being observed by an advanced civilization demands reflection on preparedness, strategy, and caution, in addition to potential physical or technological consequences. There are philosophical and ethical dimensions to consider. Being noticed could alter our approach to space exploration and communication. Should we broadcast our presence deliberately, sharing knowledge of our planet and species? Or should we exercise caution, minimizing our visibility until we better understand the intentions and capabilities of those observing us? This debate, often referred to as active SETI or messaging to extraterrestrial intelligence, remains unresolved. Some argue that any attempt to reach out could invite unknown risks, while others claim it is a natural extension of humanity's curiosity and a moral imperative too. The implications also touch on our sense of time and permanence. Unlike Earthbound history, which unfolds over centuries or millennia, interstellar events occur on vastly longer scales. The signals we send today may reach distant civilizations hundreds or thousands of years in the future. Similarly, any response might not arrive for centuries. Being found could place humanity in a long-term dialogue with an existence far beyond our own lifespans, reminding us that the universe operates on a scale far grander than our everyday experience. From a societal perspective, the knowledge that we are observed could influence culture, philosophy, and religion. For some, confirmation of extraterrestrial awareness may challenge deeply held beliefs about human uniqueness, prompting reinterpretation of our place in the cosmos. For others, it may inspire awe, curiosity, and a renewed commitment to scientific exploration. Literature, art, and music would likely reflect this new awareness, exploring themes of connection, isolation, and the search for understanding across unimaginable distances. Another profound implication lies in technological development. Knowing that advanced civilizations exist could accelerate our investment in science, engineering, and space exploration. Humanity might prioritize the creation of more sophisticated telescopes, faster spacecraft, and advanced communication systems. The awareness of being observed may act as a catalyst, uniting humanity in the pursuit of knowledge and technological achievement. In this sense, detection could serve as both a mirror and a motivator, reflecting our own potential and driving us toward greater capability. Yet, the implications are not only external. Being noticed may profoundly impact our internal understanding of life, intelligence, and existence itself. Philosophers and scientists alike may reconsider assumptions about consciousness, evolution, and the uniqueness of human experience. The realization that other intelligent beings are aware of us forces a confrontation with questions that have long been philosophical. What does it mean to be intelligent? What is the purpose of life in a universe shared with other conscious beings? And how should we interact with entities whose perspectives are likely incomprehensible to us? Even if the observers remain silent, the mere awareness of their existence could reshape our priorities and worldview. Humanity might place greater emphasis on stewardship of the planet, recognizing that our actions are now part of a broader cosmic stage. Environmental preservation, technological responsibility, and ethical governance could take on heightened significance, not only for our own survival, but also as a reflection of our civilization to distant eyes. In the realm of exploration, being noticed could redefine the way we approach interstellar travel. If we are aware that others might be watching, every probe, spacecraft, or signal becomes a statement or reflection of our capabilities and intentions. Missions like the Voyager probes, the Golden Record, and other exploratory initiatives could be seen as first steps in a dialogue across light years, a subtle introduction to our species and culture. Finally, there is the human emotional dimension. Awareness of being observed may evoke awe, wonder, humility, or even anxiety. It challenges us to expand our imagination, to consider perspectives and scales beyond ordinary experience. It also reinforces the interconnectedness of life, reminding us that, even in the vastness of space, our existence is not isolated. We are part of a dynamic, living universe, capable of reaching out, of being reached, and of understanding the profound beauty and mystery of the cosmos. In summary, the implications of being found extend far beyond scientific curiosity. They touch on ethics, philosophy, technology, society, and the deepest questions of identity and purpose. Whether we are discovered tomorrow or 1,000 years from now, the awareness that other civilizations might exist, observe, and perhaps understand us challenges humanity to think boldly, act wisely, and remain ever curious about our place in the universe. It reminds us that we are simultaneously fragile and remarkable, small yet capable of profound influence, and that in the grand tapestry of the cosmos, our story is still being written. For millennia, humans have looked up at the night sky, marveling at the stars, planets, and celestial phenomena. These distant lights have inspired awe, fear, and wonder, giving rise to myths, legends, and religious beliefs across every culture on Earth, from the ancient Sumerians and Egyptians to the Mayans and Greeks. Humans have sought to explain the mysteries of the cosmos. But could some of these stories be echoes of encounters with something more than imagination, perhaps even contact with visitors from the stars? Consider the Sumerian texts, which describe beings known as the Anunnaki, deities said to descend from the heavens to teach, guide, or influence humanity. While traditionally interpreted as mythological, some theorists suggest that these accounts may reflect ancient observations of unusual celestial events or even real extraterrestrial visitors. The tales often include detailed descriptions of flying craft, advanced knowledge, or interventions in human affairs elements that parallel modern ideas about alien contact. Similarly, in ancient Egyptian culture, gods such as Ra, Horus, and Thoth are depicted descending from the sky in elaborate chariots of fire, bearing wisdom and advanced skills. Temples, hieroglyphs, and artifacts frequently emphasize celestial connections, highlighting the reverence ancient people had for the heavens. Could these symbolic stories encode actual encounters with beings or phenomena beyond Earth? While speculative, the recurring motifs of skyborne visitors across civilizations are striking. Moving to Mesoamerican cultures, the Mayans and Aztecs recorded detailed astronomical observations, some of which included gods descending from the sky or bringing knowledge of agriculture, astronomy, and mathematics. The precision of their calendars, the alignment of pyramids with celestial bodies, and the sophistication of their astronomy suggest a deep awareness of cosmic cycles. Could these accomplishments be inspired or enhanced by guidance from external intelligences? Some researchers argue that the myths of Quetzalcoatl, the feathered serpent deity who arrived from the stars, may be interpreted as symbolic or literal evidence of encounters with ancient visitors. Across Europe, Greek and Roman mythology abounds with stories of gods and heroes interacting with mortals. Chariots of fire, lightning-wielding deities, and winged beings descending from Olympus capture the imagination, while mainstream scholars interpret these as allegorical. There is a pattern. Extraordinary events and beings originating from the sky are consistently described, suggesting a shared human fascination with the heavens. Could these narratives be cultural memories of phenomena we now struggle to explain scientifically? Even in the East, ancient Chinese and Indian texts reference celestial visitors and advanced beings. The Mahabharata, for instance, describes flying machines called vimanas, capable of moving through the sky and even engaging in battle. Ancient Chinese chronicles mention fire-breathing dragons or heavenly chariots that could, through a modern lens, be interpreted as advanced aerial phenomena or misunderstood technological devices. Across the globe, similar motifs emerge independently, a testament to humanity's shared wonder and perhaps curiosity about the stars. What connects these myths is not just their global recurrence, but their focus on the sky as a source of influence and knowledge. Across continents, people have imagined or witnessed beings descending from above, often imparting wisdom, technology, or cultural guidance. While skeptics argue these are symbolic or psychological, the consistency raises questions. Are these purely cultural inventions? Or could they be subtle memories of ancient encounters with visitors from the cosmos? Archaeologists and historians caution against assuming literal interpretations of myth, and rightfully so. Cultural narratives evolve, adapt, and are often embellished over generations. Yet, by examining patterns, shared themes, and anomalies, we can explore the tantalizing possibility that human imagination sometimes reflects something real, events or entities that defy conventional understanding. Could ancient humans, observing unusual celestial objects, meteors, or lights in the sky, have woven these experiences into their myths? Or, more provocatively, could these stories preserve hints of actual interactions with extraterrestrial visitors? Some enthusiasts point to artifacts, carvings, and iconography as potential evidence. In temples, tombs, and monuments, humans have depicted strange beings, flying machines, or celestial symbols that do not correspond easily to natural or terrestrial phenomena. While interpretations vary widely from symbolic to religious, the consistency across time and geography is intriguing. Could these images represent humanity's first attempts to record encounters with entities that came from beyond Earth? It is also possible that psychological and cultural factors played a role. Ancient civilizations often personified natural events, celestial bodies, or astronomical phenomena, imbuing them with agency. This anthropomorphizing might explain some myths while simultaneously preserving memory of extraordinary events. Even if the stories are allegorical, they reflect a profound human awareness of the sky and its mysteries, which in itself is remarkable. Ultimately, myths and legends serve as a bridge between the unknown and the familiar. They allow us to imagine possibilities, encode observations, and pass knowledge across generations. Whether these stories are purely symbolic or contain echoes of actual encounters, they highlight humanity's enduring fascination with the stars and the enduring question: have we ever truly been visited? As we explore these ancient narratives, we are reminded that human curiosity is timeless. Just as we now look through telescopes, space probes, and radio waves to search for signs of life, our ancestors looked up at the night sky, seeking meaning, guidance, and connection. The myths may be more than entertainment. They could be humanity's earliest attempt to understand its place in the cosmos and to grapple with the possibility of visitors from the stars. Long before the era of telescopes, satellites, and radio signals, humans documented unusual events in the sky. Ancient chronicles, manuscripts, and inscriptions reveal accounts of strange lights, moving objects, and celestial phenomena that defy easy explanation. While many could be natural occurrences, some descriptions are remarkably detailed and suggest something extraordinary, perhaps even evidence of visitors from beyond our solar system. Consider ancient Chinese records, which meticulously documented comets, guest stars, novae and supernova, and other celestial events. While most of these can now be explained astronomically, some entries describe bright moving objects that behave unlike known celestial bodies. In the year 643 CE, chronicles mention a fiery object that moved like a rope across the heavens before vanishing, language that today might evoke images of a UFO or spacecraft. The consistency and detail of such accounts across centuries indicate that observers were attempting to capture real phenomena, even if they lacked the scientific tools to fully understand them in Europe. Medieval manuscripts recount similar anomalies. Monks, scholars, and chroniclers describe sky battles, celestial armies, and chariots of fire moving through the night, while often interpreted as allegory or religious symbolism. The frequency and vividness of these accounts invite speculation. Could some of these events have been interactions with intelligent beings, misinterpreted through the lens of human culture and mythology? Or were they glimpses of advanced technology, transient and mysterious? Mesoamerican civilizations also recorded unusual aerial phenomena. Codices, such as the Dresden Codex, depict strange disks, glowing objects, and entities in the sky. Some researchers suggest these may represent astronomical events. But the recurring presence of strangers from the sky or unusual craft could also hint at observations of unknown visitors. These accounts are particularly fascinating because they often coincide with descriptions of deities descending to impart knowledge or influence human affairs, blurring the line between myth and historical record in Middle Eastern texts, such as the Quran and earlier Babylonian chronicles. Celestial signs play a significant role in human affairs. Stars, meteors, and fire in the sky are frequently described as omens or messages from higher powers, while ancient cultures interpreted these phenomena symbolically. Modern readers may speculate that they could reflect actual observations of anomalous objects. For example, accounts of flaming wheels or lights moving against the wind may correspond to sightings of objects unlike any natural astronomical body, even Renaissance Europe presents compelling anecdotes. During the 15th and 16th centuries, numerous eyewitness reports describe luminous spheres, triangular formations, and other aerial anomalies. One notable example comes from 1561 in Nuremberg, Germany, where residents witnessed a mass of bright objects in the sky, engaging in what appeared to be a battle. While interpretations vary from atmospheric phenomena to social hysteria, specificity and number of eyewitnesses make it a striking case. Could such events be early documentation of extraterrestrial activity? Beyond individual sightings, some scholars point to patterns of recurrence in historical records. Certain regions report more frequent phenomena, suggesting either a higher rate of natural activity or perhaps repeated visitation by intelligent entities. For example, sightings of unexplained aerial lights have been recorded in ancient Britain, Scandinavia, China, and the Americas independently and across millennia. While coincidence cannot be ruled out, the geographic and temporal spread raises intriguing questions about the possibility of persistent, observable phenomena originating from beyond Earth, in addition to textual records. Art and iconography often reflect these unexplained observations. Cave paintings, rock carvings, and ancient murals sometimes depict figures interacting with radiant objects or beings descending from the sky. While interpretations remain speculative, the imagery hints at sustained human fascination with anomalous aerial events. Could these representations preserve collective memory of actual visitors abstracted through artistic expression? Or do they reflect a universal human tendency to personify and mythologize the unknown? Another compelling source comes from early astronomers and navigators. During the age of exploration, sailors often recorded lights on the horizon, fast-moving objects, and other atmospheric anomalies, though many were attributed to weather comets or optical illusions. Some reports describe intelligent behavior, objects changing course, performing maneuvers, or disappearing instantly. While anecdotal, the consistency of these observations across cultures and oceans adds weight to the mystery. Modern studies of these historical accounts often focuses on patterns, correlations, and natural explanations, such as meteor showers, auroras, comets, or atmospheric optics. Yet, despite these efforts, certain reports resist simple categorization. Descriptions of structured movement, intelligent coordination, or craft-like behavior recur in records from different times and continents. While no single account proves extraterrestrial visitation, the collective body of evidence paints a picture of human experience that includes a persistent awareness of unusual celestial phenomena. It is also important to consider the context in which these observations occurred. Ancient and medieval observers lacked modern technology, but possessed keen powers of observation. Star charts, almanacs, and calendars suggest careful monitoring of the skies. Deviations from expected patterns, strange lights, objects moving independently of stars or planets would have stood out vividly. Their detailed record-keeping implies that anomalies were significant enough to warrant attention, reflection, and documentation. Finally, reflecting on historical accounts offers a valuable lesson. Human curiosity and observation are timeless. Our ancestors' records, whether mythologized, religious, or purely descriptive, highlight a continuous effort to make sense of the unknown. These chronicles may contain echoes of phenomena we are only beginning to study scientifically, bridging past and present in our ongoing quest to understand whether we have ever truly been visited. By examining these historical records, we gain perspective not only on human perception, but also on the enduring question: have extraterrestrial visitors left traces in our shared history? While definitive proof remains elusive, the consistency, detail, and global scope of these accounts keep the possibility alive, inviting modern researchers to explore the interface between myth, observation, and the unexplained. Having explored myths, legends, and historical accounts of unexplained celestial phenomena, the question naturally arises: how should we interpret these ancient encounters? Modern science provides tools to analyze, contextualize, and sometimes demystify these records. Yet there remains room for wonder, speculation, and interdisciplinary study. One approach is astronomical contextualization. Many ancient accounts can now be understood through natural celestial events: comets, meteor showers, planetary alignments, auroras, and supernova would have appeared both spectacular and unfamiliar to observers lacking modern instruments. A fiery chariot streaking across the sky might simply have been a meteor. Yet the language and interpretation of the event reflect humanity's attempt to make sense of the extraordinary. Science allows us to separate natural explanations from those that remain anomalous, but it cannot always resolve ambiguity. Another perspective comes from anthropology and cultural studies. Myths and legends are not merely stories. They encode cultural values, social norms, and cosmological understanding. By examining patterns, motifs, and shared themes, researchers can identify which elements reflect natural observation, which are symbolic, and which may hint at something more unusual. For instance, depictions of beings descending from the sky might symbolize divine authority, technological knowledge, or, intriguingly, encounters with entities that inspired awe. Anthropology reminds us that interpretation is influenced by culture, worldview, and context. The modern UFO phenomenon provides an additional lens for interpretation. Reports of unexplained aerial phenomena today often echo ancient descriptions: luminous objects, unconventional movement, and perceived intelligence behind the motion. While contemporary sightings may involve misidentified aircraft, atmospheric phenomena, or hoaxes, the parallels with historical accounts are striking. This continuity across millennia raises questions about the persistence of such phenomena and the possibility that humans have been observing unusual objects in the sky for thousands of years. Archaeological evidence also offers tantalizing clues. Certain ancient structures, such as the pyramids of Giza, Stonehenge, and the Nazca Lines, demonstrate precise astronomical alignments. While traditional explanations focus on religious, calendrical, or ceremonial purposes, some researchers propose that these alignments may indicate knowledge imparted by visitors or observation of unusual celestial events. While these ideas are controversial and speculative, they invite consideration of the ways in which humans might have responded to extraordinary stimuli in the sky. Interdisciplinary approaches, combining archaeology, astronomy, history, and anthropology, allow for nuanced interpretations. For example, studying ancient inscriptions alongside astronomical reconstructions can reveal whether reported phenomena correspond to identifiable events, such as eclipses or comet appearances. Conversely, anomalies that resist explanation might point to truly unusual occurrences. This method respects both scientific rigor and the imaginative possibilities of human history. It is also worth considering psychological factors. Humans have an innate tendency to seek patterns, attribute agency, and create narratives to explain the unknown. This tendency could account for some encounters being mythologized over time. However, psychological explanations do not necessarily negate the potential for actual anomalous events. Rather, they highlight the complex interplay between observation, memory, and storytelling. Ancient peoples interpreted extraordinary events through the lenses of their knowledge and culture, just as we do today. Another intriguing avenue is the study of technosignatures in history. Some theorists suggest that certain descriptions of lights, crafts, or sky chariots may represent encounters with technology far beyond the understanding of the observer. While speculative, this hypothesis aligns with modern concepts of SETI and technosignatures, observing the traces of advanced civilizations, whether deliberate or incidental, through their impact on the environment, culture, or artifacts. Ancient observers might have been the first to document such signatures. Even if their understanding was framed in the language of myth, modern science emphasizes skepticism, balanced with curiosity. Not every myth or historical account points to extraterrestrial visitation. Yet dismissing all as purely symbolic may overlook patterns worthy of study. Scholars today often focus on identifying which phenomena can be explained naturally and which remain anomalous. By cataloging reports, analyzing consistency across cultures, and comparing historical descriptions with known astronomical events, researchers can separate the probable from the possible, leaving a small but intriguing window for speculation. The cultural impact of ancient encounters, whether literal or metaphorical, cannot be understated. These stories shaped belief systems, inspired technological curiosity, and influenced human imagination. They remind us that the sky has always been a canvas for human creativity and inquiry, even if extraterrestrial visitation is never confirmed. The myths and accounts reflect a universal human desire to reach beyond our world and understand our place in the cosmos. Finally, interpreting ancient encounters challenges modern humanity to reflect on its own perspective. We are now capable of observing the universe in unprecedented detail, from deep space telescopes to interplanetary probes. By juxtaposing modern observation with ancient documentation, we can appreciate both the continuity of human curiosity and the enduring mystery of the sky. We learn that humanity has always sought connection, meaning, and understanding in the cosmos, and that our ancestors' attempts, whether myth, legend, or historical observation, remain part of a continuum that stretches across millennia. In conclusion, interpreting ancient encounters requires a delicate balance of scientific rigor, cultural sensitivity, and imaginative openness. By examining myths, historical accounts, and archaeological evidence, we uncover patterns that illuminate both the human mind and the universe itself. Whether these accounts reflect natural phenomena, symbolic storytelling, or genuine interaction with visitors from beyond, they provide invaluable insight into humanity's enduring quest to understand the unknown. Through this lens, we see that our fascination with the stars is not new. It is a timeless, shared experience that connects us with our ancestors and, perhaps, with beings that might still watch us from the cosmos. The idea of traveling beyond our solar system has long captivated human imagination. From science fiction tales to ambitious scientific proposals, interstellar travel represents one of the ultimate frontiers of exploration. Yet the challenges are profound, spanning physics, engineering, biology, and human psychology. Before imagining contact with distant civilizations, we must first understand the difficulties inherent in leaving the familiar confines of our sun's gravitational domain. At the most basic level, distance is the primary obstacle. The nearest star system, Alpha Centauri, lies approximately 4.37 light-years away. To put this in perspective, the fastest spacecraft humanity has ever built, New Horizons, launched in 2006, travels at roughly 16 kilometers per second. At that speed, reaching Alpha Centauri would take over 78,000 years. Even if we could build craft capable of traveling at 0.10% the speed of light, the journey would still span decades. The immense scale of interstellar distances demands propulsion systems far beyond our current capabilities. Propulsion technology is at the heart of the challenge. Traditional chemical rockets, which serve us well for planetary travel, are woefully inadequate for interstellar distances. Alternative methods, such as nuclear fusion engines, antimatter propulsion, and light sails, are under study but remain largely theoretical or in early experimental phases. Fusion engines, for example, could provide continuous acceleration over years, potentially reaching significant fractions of the speed of light. Yet containment of the reaction, fuel supply, and heat dissipation present formidable engineering hurdles. Light sail technology, proposed by initiatives like Breakthrough Starshot, offers another intriguing possibility. By harnessing powerful laser beams from Earth to push ultra-lightweight spacecraft, this method could accelerate tiny probes to 20% of the speed of light, while promising for sending small instruments. Scaling this technology for crewed missions presents enormous challenges, including structural integrity, shielding from interstellar particles, and long-term life support. The interstellar medium itself poses additional risks. Space between stars is not empty. It contains dust, gas, and high-energy cosmic rays. At relativistic speeds, even tiny particles can generate catastrophic damage upon impact. Shielding spacecraft effectively against these hazards without adding prohibitive mass is a critical engineering problem. Additionally, navigation through the interstellar medium requires precise instruments capable of detecting and avoiding debris over vast distances, a task that grows exponentially complex the further we travel. Life support and human biology add another layer of complexity. A journey spanning decades or centuries demands sustainable life support systems capable of recycling air, water, and food. Psychological well-being is equally crucial. Long duration, isolation, confinement, and distance from Earth can cause severe stress, depression, or cognitive decline. Proposals for interstellar crews often involve multi-generational missions, where descendants of the original travelers continue the voyage. This raises profound questions about social structure, governance, and ethics across generations. Energy supply is another central concern. Current spacecraft rely on solar panels, radioisotope, thermoelectric generators, or chemical fuel. In the depths of interstellar space, sunlight becomes negligible and compact. Long-lasting energy sources are necessary to maintain propulsion, life support, and communication. Nuclear reactors, advanced batteries, or even theoretical matter-antimatter systems are potential solutions. But each carries technological and safety challenges. Communication across light years further complicates interstellar missions. Signals travel at the speed of light, meaning messages to and from Alpha Centauri would take over 4 years each way. For distant systems, delays stretch decades, effectively isolating crews from Earth-based guidance or support. Autonomous decision-making becomes essential, requiring sophisticated artificial intelligence and onboard problem-solving capabilities, beyond technological and physical barriers. Time dilation and relativistic effects introduce unique challenges. Traveling near the speed of light changes the passage of time relative to observers on Earth, while time dilation can allow travelers to experience shorter subjective durations. It complicates mission planning, navigation, and coordination with Earth-based operations. Accurate modeling of relativistic effects is essential to prevent navigational errors and to synchronize communication across vast distances. Societal and financial factors are equally significant. Interstellar missions would require unprecedented international collaboration, funding, and public support. Building infrastructure, developing advanced propulsion, and ensuring crew safety would likely cost trillions of dollars, stretching decades of research, engineering, and political commitment. Sustained global interest is necessary to see projects of this scale to completion. Despite these challenges, scientific progress continues to push the boundaries. Advances in material science, energy storage, autonomous AI systems, and nanotechnology make aspects of interstellar exploration increasingly feasible. Concepts once confined to imagination ultralight probes, relativistic travel, or robotic explorers venturing into nearby star systems are now subjects of serious study. The obstacles remain formidable, but humanity's relentless curiosity and ingenuity continue to close the gap between dream and reality. Interstellar travel is not merely an engineering problem, it is a test of human resilience, creativity, and foresight. Every challenge: distance, propulsion, life support, energy, navigation, and communication forces us to reconsider what it means to explore. These obstacles also offer opportunities for innovation, potentially yielding technologies that benefit Earth as much as they enable journeys beyond it. Finally, considering the science of interstellar travel brings us back to the question of extraterrestrial observers. If reaching other star systems is so difficult for us, how might advanced civilizations have managed it? Could objects like Oumuamua or 3I Atlas represent evidence of probes from distant civilizations, traversing the galaxy on missions of exploration, observation, or communication? Understanding the challenges we face offers a framework to speculate responsibly about the possibilities, if they exist. These civilizations would have to solve problems similar to our own, but on a scale and with resources that may far exceed our current imagination. In essence, the science of leaving our solar system bridges the known and the speculative. It grounds our curiosity in physics, engineering, and biology while inviting questions about life beyond Earth. By confronting the immense challenges of interstellar travel, we gain perspective on both our technological limits and our aspirations, on what is possible today and what may one day become reality. Understanding these challenges helps us frame the broader narrative. The universe is vast, and the journey to meet or be noticed by others is as complex as it is profound. Exploring the cosmos beyond our solar system requires more than determination. It demands innovation, a deep understanding of physics, and radical advancements in propulsion technology. While interstellar travel is daunting, scientists and engineers have conceived a range of concepts that, if realized, could allow humanity to journey across the stars. Chemical rockets, our primary tool for space travel, are fundamentally inadequate for interstellar missions. They rely on the combustion of fuel to generate thrust, but the energy density of chemical propellants is minuscule compared to the vast distances between stars. To reach even a fraction of light speed, a spacecraft would need more fuel than is physically practical to carry, making alternative propulsion methods essential. One promising avenue is nuclear propulsion, which leverages the immense energy stored within atomic nuclei. There are two main approaches: nuclear thermal rockets and nuclear fusion engines. Nuclear thermal rockets heat a propellant, such as hydrogen, using a nuclear reactor, expelling it at high velocity to generate thrust. This method provides far greater efficiency than chemical rockets, allowing spacecraft to achieve higher speeds within the solar system and potentially to nearby star systems. Nuclear fusion propulsion takes this a step further. Fusion, the same process powering the Sun, releases enormous amounts of energy from light atomic nuclei, such as hydrogen isotopes. Conceptual designs like the Daedalus and Longshot projects propose accelerating spacecraft to a significant fraction of light speed using fusion-driven engines. Challenges remain immense, including containing the reaction, managing waste heat, and supplying sufficient fuel. Yet the theoretical performance makes interstellar travel conceivable within decades rather than millennia beyond nuclear energy. Antimatter propulsion presents another tantalizing possibility. When matter and antimatter collide, they annihilate each other, releasing energy with near-perfect efficiency according to Einstein's equation. E equals mc. This energy density far exceeds any chemical or nuclear source. In principle, a small quantity of antimatter could accelerate a spacecraft to relativistic speeds. The main hurdles are producing, storing, and controlling antimatter safely, a task that remains beyond current technology. Though research continues in particle physics laboratories, photon or light sails provide a non-chemical approach to propulsion. These ultra-thin reflective sails are pushed by the momentum of photons, typically generated by high-powered lasers on Earth or in space. Initiatives such as Breakthrough Starshot aim to accelerate gram-scale probes to 20% of light speed within decades, demonstrating that interstellar travel does not require massive fuel stores. For larger crewed vessels, scaling the concept is far more complex, requiring enormous laser arrays and innovative materials capable of withstanding intense radiation. The physics of relativistic travel also imposes fundamental limits. According to Einstein's special relativity, as an object approaches the speed of light, its mass effectively increases, requiring exponentially more energy to accelerate further. This means no spacecraft with mass can reach or exceed light speed, though traveling at 50 to 90% of light speed remains theoretically achievable. Understanding these constraints is crucial for planning interstellar missions and estimating travel times to nearby star systems. Warp drives and space-time manipulation have captured the imagination of both scientists and science fiction writers. Concepts like the Alcubierre drive propose compressing space in front of a spacecraft and expanding it behind, effectively allowing faster-than-light travel without violating relativity locally. While mathematically intriguing, these ideas currently face extreme energy requirements and require exotic forms of matter that have not been observed. Nevertheless, they illustrate the bold thinking needed to overcome interstellar distances. Another fascinating concept is magnetic and electric field propulsion. Electromagnetic propulsion uses charged particles or plasma accelerated by magnetic fields to generate thrust. Theoretically, such systems could continuously accelerate a spacecraft over long durations, achieving high velocities without the massive fuel burdens of conventional rockets. Concepts like the M drive, although controversial, continue to spark debate and experimental inquiry, highlighting humanity's willingness to explore unconventional solutions. Hybrid approaches combine multiple propulsion methods to optimize efficiency. For example, a spacecraft might use chemical rockets to escape Earth, nuclear thermal propulsion for interplanetary travel, and light sails for the interstellar leg. These combinations acknowledge the limitations of any single method while leveraging the strengths of each, reflecting a pragmatic path toward feasible interstellar exploration. Interstellar navigation presents another challenge intertwined with propulsion. At high velocities, even tiny miscalculations can result in vast deviations over light years. Advanced guidance systems must incorporate real-time astronomical data, autonomous decision-making, and perhaps even AI capable of handling unforeseen obstacles. Radiation hazards, interstellar dust, and micrometeoroids require robust shielding strategies, further complicating spacecraft design. Timescales and mission planning are central to any interstellar endeavor. Even with advanced propulsion, journeys to nearby stars would span decades or longer. Multi-generational missions, where crews live, reproduce, and die aboard the spacecraft, raise profound ethical and logistical questions. Alternatively, unmanned probes, capable of rapid acceleration and autonomous operation, could precede human missions, providing reconnaissance and data about distant systems. The potential payoff, however, is extraordinary. Achieving interstellar travel could allow humanity to directly study exoplanets, search for life beyond Earth, and potentially encounter civilizations that have solved the same challenges. It would transform our understanding of physics, engineering, and biology, while reshaping our place in the universe. Finally, understanding these propulsion challenges and possibilities provides a lens through which we can view Oumuamua, 318LAS, and other interstellar visitors. Objects traveling through our solar system at unusual velocities and trajectories may not merely be natural bodies. They could represent probes or craft employing advanced propulsion beyond our current capabilities. By studying the physics of interstellar travel, we gain insight into what is technically feasible and what signs might indicate the presence of intelligent extraterrestrial travelers. In conclusion, the science of propulsion and interstellar physics demonstrates that reaching the stars is no small feat. The hurdles are immense, requiring mastery of energy generation, material science, navigation, and human biology. Yet the combination of nuclear antimatter, light sail, and exotic theoretical methods suggests that interstellar travel, once considered impossible, lies within the realm of future possibility. By understanding these challenges, we can begin to speculate responsibly about the nature of objects and phenomena that visit or traverse our solar system, and perhaps consider the ways in which advanced civilizations might navigate the cosmos. As humanity grapples with the immense challenges of leaving our solar system, we must consider a tantalizing possibility. Might other civilizations have already solved these problems and visited us? Observations of interstellar objects such as Oumuamua and 3I Atlas have reignited this question, prompting both scientists and the public to wonder whether extraterrestrial visitors have left subtle traces in our cosmic neighborhood. In October 2017, the astronomical community observed a peculiar object entering our solar system from interstellar space, Oumuamua. Its elongated shape, unusual rotation, and unexpected acceleration defied conventional explanations. Unlike typical comets or asteroids, Oumuamua displayed no visible outgassing, yet accelerated as though affected by some force. While many explanations, ranging from a fragment of a distant planetary system to a natural rock with unusual properties, remain plausible, some scientists have speculated that Oumuamua could be a technological artifact, perhaps a probe sent by an advanced extraterrestrial civilization. Oumuamua's trajectory adds to the mystery. Its path through the solar system was hyperbolic, indicating it was not gravitationally bound to our Sun. The object appeared to be on a one-way journey, likely having traversed thousands of light-years before its brief encounter with Earth. This extraordinary voyage underscores the feasibility of interstellar travel for small, unmanned probes, a strategy that highly advanced civilizations might employ to explore distant star systems. Following Oumuamua, astronomers discovered 3I Atlas in 2019, another interstellar object entering our solar system. Unlike Oumuamua, 3I Atlas behaved more like a typical comet, exhibiting a tail and outgassing. Yet its mere interstellar origin sparked renewed interest in the possibility that some interstellar objects could be intentionally sent by alien civilizations. The discovery of multiple interstellar visitors suggests that the galaxy may be peppered with objects capable of traversing vast distances. Whether natural or artificial, the idea of extraterrestrial probes aligns with concepts discussed in the context of breakthrough Starshot and other interstellar propulsion studies. Small, lightweight autonomous probes could travel to neighboring star systems, gather data, and even relay information back to their origin civilization. If a highly advanced civilization exists, it might already have dispatched such probes, some of which could be passing through our solar system unnoticed. Observations like Oumuamua could represent rare glimpses of such technologies. Yet what evidence would indicate an alien origin versus a natural interstellar object? Scientists consider several criteria: unusual trajectories, unexpected acceleration, non-standard rotation, and physical characteristics that defy known cosmic bodies. For example, Oumuamua's cigar-like shape, high reflectivity, and lack of visible gas emissions were anomalous compared to typical asteroids or comets. While natural explanations remain plausible, these characteristics invite speculation about advanced technology beyond physical observation. The timing and frequency of interstellar visitors could suggest deliberate exploration. If objects like Oumuamua and 3I-ATLAS are more common than previously thought, it raises questions about the density of interstellar traffic. Are these objects randomly distributed, or might they represent intentional surveys of nearby planetary systems, including ours? Advanced civilizations might employ automated reconnaissance probes, capable of moving between star systems over centuries or millennia, with minimal maintenance. The concept of stealth or observational probes is also worth considering. Highly intelligent civilizations might send devices designed to avoid detection while monitoring emerging technological species like humanity. Such probes could operate for centuries, using small-size, reflective surfaces or unconventional propulsion to minimize visibility. In this scenario, Oumuamua might have been an example of an intentional but transient encounter, its fleeting appearance providing us only a brief glimpse of what may be a much larger network of exploratory devices. Scientific caution is critical. Mainstream explanations for Oumuamua's and 3I-ATLAS's behavior still lean toward natural phenomena. For instance, Oumuamua's acceleration could result from outgassing of volatile compounds, albeit in an unusual manner. However, considering the possibility of alien visitors encourages creative thinking, inspires new observational strategies, and reminds us that our understanding of the cosmos is incomplete. Even if we never conclusively identify an artificial origin, the exercise sharpens our methods for detecting subtle anomalies. The potential for interstellar communication is another dimension to explore. If alien civilizations are sending probes, could they also be attempting contact? Signals, whether electromagnetic or otherwise, might be embedded in the path's rotations or surface properties of interstellar objects. While highly speculative, some scientists have proposed searching for encoded light pulses, unusual radiation patterns, or reflective surfaces as indicators of intelligent design. Such studies lie at the intersection of astronomy, set search for extraterrestrial intelligence, and planetary science. Moreover, considering alien visitors reshapes our understanding of cosmic timelines. Humanity has existed for only a fraction of Earth's history. Advanced civilizations, if they exist, could predate us by millions of years. They would have had ample time to develop interstellar technology, dispatch probes, and observe emerging planets. In this context, our first encounters with interstellar objects might be the earliest hints that we are being noticed, even if indirectly. Finally, pondering alien visitors invites reflection on humanity's future in interstellar exploration. By studying the physics, engineering, and potential strategies of advanced civilizations, we can better understand the possibilities and limitations of our own technological path. Could we one day launch probes of our own to neighboring star systems, or even encounter visitors from distant civilizations? Observations like Oumuamua and 3I-ATLAS are both a scientific puzzle and a profound inspiration, bridging our curiosity with the broader question of life beyond Earth. In conclusion, The study of interstellar objects like Oumuamua and 3I Atlas illustrates the intersection of observation, physics, and speculation. While definitive proof of alien visitation remains elusive, these objects encourage rigorous scientific inquiry and imaginative exploration. By analyzing their properties, trajectories, and anomalies, we learn not only about the cosmos, but also about the challenges and possibilities of interstellar travel. Whether natural or artificial, these celestial visitors remind us that the universe is vast, dynamic, and potentially inhabited by civilizations far more advanced than our own. The night sky has always captivated humanity, inspiring both awe and curiosity. For centuries, we have looked upward, wondering whether other intelligent beings might exist beyond Earth. Modern science has transformed this curiosity into systematic efforts, particularly through the study of extraterrestrial signals, which might reveal the presence of civilizations elsewhere in the galaxy. Understanding these efforts provides a framework to consider whether we might be observed or even contacted by beings beyond our solar system. The most established approach is the search for extraterrestrial intelligence, SETI. Founded in the 1960s, SETI combines astronomy, engineering, and computer science to monitor the skies for electromagnetic signals that exhibit patterns inconsistent with natural phenomena. Radio waves, for example, can traverse vast interstellar distances with minimal absorption, making them ideal candidates for interstellar communication. Scientists use arrays of radio telescopes to scan targeted star systems, listening for narrowband signals or bursts of energy that might indicate an intelligent source. A key principle in CDI is distinguishing artificial signals from cosmic noise. Space is filled with natural sources of radio waves, including pulsars, quasars, and solar emissions. Signals of interest often exhibit narrow frequency bands, repetition, or modulation that suggest intentional design. One famous example is the 1977 WOW signal detected by the Big Ear radio telescope. This 72-second burst of radio waves from the constellation Sagittarius remains unexplained, sparking speculation about its origin. While no definitive conclusion was reached, the signal underscores the difficulty of confirming extraterrestrial communication and the tantalizing possibility that intelligent messages may be fleeting or intermittent. Beyond radio waves, researchers consider optical signals, such as laser pulses, as potential markers of intelligent life. Lasers can be tightly focused and delivered across interstellar distances with minimal dispersion. Projects like the Optical SETI initiative aim to detect such high-intensity, short-duration light flashes, which could function as beacons or information carriers. Optical signals offer advantages over radio waves, including lower background noise and the ability to encode complex information. Yet they require precise targeting and timing to be detected by observers like us. Another frontier involves technosignatures, which encompass any evidence of technological activity beyond Earth. Unlike conventional SETI, which focuses on intentional messages, technosignature research searches for indirect indications of advanced civilizations. Examples include unusual atmospheric compositions, megastructures, or large-scale energy use detectable across light years. A Dyson sphere, for instance, a hypothetical structure enclosing a star to harness its energy, would produce distinctive infrared radiation patterns. Observing such anomalies could hint at civilizations capable of interstellar travel or communication. Even if they have never deliberately contacted us, the challenge of detection is formidable. Interstellar distances introduce delays in signal arrival times. A civilization 100 light-years away sends a message that we might receive a century later, long after it was transmitted. Moreover, signals may be brief, directional, or infrequent, requiring sustained monitoring and advanced algorithms to identify them. Modern SETI projects employ machine learning and data mining techniques to sift through vast quantities of data. searching for patterns that human analysts might overlook, understanding. The probability of contact also involves the Drake equation, formulated in 1961 by Frank Drake. This equation estimates the number of communicative civilizations in the galaxy based on factors such as star formation rates, planetary habitability, and the longevity of technological societies. While many variables remain uncertain, the equation frames our search scientifically, suggesting that even if civilizations exist, the odds of simultaneous detection may be low. Yet not zero that the search for extraterrestrial signals is not limited to distant stars. Nearby planets and moons within our solar system also offer possibilities. While no evidence of intelligent life has been found on Mars, Europa, or Enceladus, these bodies may harbor microbial life or past biosignatures. Understanding local environments aids in refining our expectations for detecting signals across interstellar space. A civilization that has mastered interstellar travel would likely leave traces beyond its home system, potentially providing indirect evidence of its existence. Ethical and philosophical questions emerge alongside scientific considerations. If we detect an alien signal, how should humanity respond? Should we broadcast our presence or remain silent to avoid potential risks? International protocols, such as those established by the SETI Post-Detection Task Group, suggest cautious verification, global consultation, and careful communication planning. These guidelines reflect the profound implications of detecting signals from distant civilizations, highlighting both the promise and the responsibility inherent in our search. Finally, the search for extraterrestrial signals is an ongoing testament to human curiosity and ingenuity. By combining astronomy, physics, engineering, and computation, we extend our senses across light years, listening for the faint whispers of distant civilizations. Even in the absence of confirmed contact, the search inspires technological advances, global collaboration, and a deeper appreciation for our place in the cosmos. In conclusion, the systematic search for extraterrestrial signals, whether through radio waves, optical pulses, or technosignatures, forms a cornerstone of humanity's quest to understand whether we are alone. The strategies, challenges, and philosophical considerations of this search provide the context for imagining how alien civilizations might observe us, and whether our own efforts to detect them are mirrored by distant observers. By exploring these signals, we not only probe the stars, but also reflect on our own identity as a species capable of reaching outward, listening and contemplating the universe beyond our home planet. As we ponder the possibility of extraterrestrial civilizations, a natural question arises. If advanced beings exist, could they already be observing us? The idea that Earth might be under surveillance, whether intentionally or inadvertently, requires consideration of both technological capabilities and the signals our planet emits. Understanding these factors helps frame the broader search for extraterrestrial intelligence and guides our expectations for potential encounters. One of the most obvious ways we might be observed is through electromagnetic emissions. Since the early 20th century, humanity has broadcast radio and television signals into space. Over time, these signals have formed a faint sphere of communication, expanding outward at the speed of light. A civilization with sufficiently sensitive instruments could detect the unique patterns of artificial transmissions, recognizing them as the product of an intelligent species. While these signals weaken with distance, they offer a potential breadcrumb trail pointing toward technologically active worlds. Radar, missions, and other high-intensity signals also contribute to our detectability. Powerful radars, such as those used for planetary mapping or asteroid tracking, emit focused beams of energy that could, in theory, be intercepted by distant observers. Unlike broad radio broadcasts, these signals are more concentrated and could carry distinctive patterns, potentially revealing the presence of an industrialized civilization. While these emissions are sporadic and directional, They might still be detectable by an advanced society using long-range observational technologies. Another potential avenue for observation involves optical and infrared signatures. Cities and industrial activity produce heat, which radiates as infrared energy. From space, concentrated areas of light or heat could be interpreted as signs of technological activity. In the context of exoplanet research, scientists already search for unusual atmospheric compositions or thermal anomalies that might indicate life or industrial processes. A civilization capable of observing Earth with sufficient resolution could detect these indicators, especially at night when artificial lighting contrasts sharply with natural darkness. Beyond passive observation, advanced civilizations might employ interstellar probes designed to monitor emerging technological species. As discussed with Oumuamua and 3I ATLAs, small autonomous craft could traverse vast distances, gathering data without directly interacting with inhabitants. Such probes might carry sensors capable of analyzing electromagnetic emissions, atmospheric composition, and surface structures, providing a detailed understanding of planetary civilizations while remaining undetected. The brief encounters of interstellar objects with unusual trajectories could, in part, be interpreted as examples of such observation. Gravitational and orbital monitoring represents another subtle form of surveillance. Precise instruments could detect variations in planetary motion, atmospheric density, or magnetic fields, indirectly revealing the presence of human activity. For instance, satellites, space stations, and other artificial structures alter a planet's electromagnetic or gravitational profile. Observers equipped with sensitive instruments might infer our technological advancement based on these anomalies. Even without direct contact, signals embedded in natural phenomena offer a fascinating speculative scenario. Some scientists have hypothesized that advanced civilizations might employ methods that leave detectable patterns in otherwise natural signals. For example, a carefully modulated light pulse, subtle gravitational wave disturbances, or engineered trajectories of interstellar objects could serve as messages or surveillance tools. While highly theoretical, such strategies illustrate the ingenuity required for observing a civilization without interfering. Overtly, humanity's own observations of the cosmos offer insight into what an extraterrestrial civilization might notice. Just as we detect exoplanets via transit methods, spectroscopic analysis, and light curves, a sufficiently advanced society could study Earth's orbital characteristics, atmospheric composition, and seasonal variations. Evidence of life such as oxygen-rich atmospheres or the presence of industrial pollutants could signal our existence long before any direct interaction occurs. This perspective frames Earth as a detectable entity in the galaxy, especially for civilizations employing technologies more sophisticated than our own. SETI and METI, messaging extraterrestrial intelligence, also play a role in understanding how we might be observed. SETI focuses on listening for incoming signals, while METI involves deliberate transmissions intended for extraterrestrial civilizations. While METI projects remain controversial due to potential risks, they illustrate the principle that intelligent species can intentionally reveal themselves. If other civilizations use similar strategies, Earth might already be within their observational range, receiving attention comparable to our own signals into space. Technological asymmetry is a crucial factor. If extraterrestrial civilizations are thousands or millions of years more advanced than humanity, their observational capabilities may vastly exceed ours. They could employ methods that are undetectable by current human instruments, silently monitoring our communications, energy usage, and planetary changes without leaving discernible traces. This asymmetry suggests that even if we have not observed them directly, it remains plausible that they are aware of us. Finally, the question of observation intersects with philosophical and ethical considerations. If we are being watched, What does it mean for humanity's autonomy and future choices? Awareness of observation could influence how we manage technology, communicate, and explore the cosmos. Understanding potential observation methods helps us anticipate scenarios, develop strategies for detection, and reflect on our role in the broader galactic community. In conclusion, the possibility that extraterrestrial civilizations might observe Earth is grounded in both current scientific understanding and speculative reasoning. Electromagnetic emissions, optical and infrared signatures, interstellar probes, and gravitational monitoring all offer potential pathways for detection. By analyzing these mechanisms, we not only assess the likelihood of being observed, but also gain perspective on our own technological footprint, whether passive or deliberate. The study of observation illuminates the subtle interplay between civilizations across the stars, reminding us that our existence might resonate far beyond our own solar system. As humanity continues to search for extraterrestrial intelligence, the next critical challenge lies in interpreting the signals we might receive. Even if a signal is detected, discerning whether it is of artificial origin, understanding its meaning, and distinguishing it from natural phenomena present immense scientific and philosophical challenges. These considerations form the bridge between observation and understanding, transforming potential encounters into meaningful knowledge. One of the first steps in signal interpretation is verification. Signals from space can originate from a wide variety of sources, both cosmic and terrestrial. Pulsars, quasars, solar flares, and cosmic background noise can all mimic patterns that might initially appear artificial. Additionally, human-generated interference, such as satellites, aircraft communications, or terrestrial radio transmissions, can create false positives. Verification requires multiple independent observations, ideally from geographically separated observatories, to confirm that the signal is indeed extraterrestrial and not a local artifact. Once a signal is verified, scientists consider its structure and patterning. Natural signals tend to exhibit predictable, often continuous characteristics, whereas artificial signals may show regularity, repetition, or modulation suggestive of intentional encoding. For instance, narrowband radio emissions or rapidly repeating pulses could indicate a deliberate communication attempt. Advanced civilizations might employ encoding strategies far beyond our comprehension, including frequency modulation, polarization patterns, or temporal sequences designed to maximize the likelihood of detection by intelligent species. The next challenge is decoding and interpretation. Even if a signal is identified as artificial, its meaning may remain elusive. Humans face the difficulty of understanding communication from a civilization with potentially vastly different sensory modalities, cognitive frameworks, and conceptual structures. A signal might convey information mathematically, visually, or through patterns of energy we have yet to conceive. Mathematic constants, such as prime numbers, have often been proposed as universal languages to indicate intelligence. Yet a complete translation may require profound ingenuity and patience. False positives and ambiguous signals pose a constant threat to interpretation. For example, the famous 1977 WOW signal displayed characteristics consistent with an artificial origin but never repeated, leaving its meaning unresolved. Other potential signals may be transient, distorted by interstellar medium effects, or modified by unknown physical processes. Scientists must apply rigorous statistical and physical analysis to differentiate between genuine messages and coincidental patterns. Recognizing that initial excitement may be tempered by uncertainty, the context of detection is equally important. Signals observed from interstellar objects, exoplanet systems, or localized cosmic phenomena must be interpreted in light of their origin and trajectory. Anomalous behavior, such as unexpected acceleration of interstellar objects or unusual spectral signatures, may indicate deliberate manipulation or information encoding. By studying these contexts, researchers can prioritize which signals warrant deeper investigation, distinguishing potential communications from cosmic coincidences. Machine learning and artificial intelligence are increasingly critical tools in signal interpretation. The sheer volume of data collected by modern telescopes, satellites, and sensors exceeds human processing capacity. AI algorithms can identify patterns, detect anomalies, and flag candidate signals for human analysis. Advanced neural networks may even suggest potential decoding strategies, exploring vast combinatorial possibilities that would be impractical for human researchers alone. These tools augment our ability to discern subtle, intelligent patterns embedded within the cosmic noise. Interpreting potential acute signals also involves consideration of extraterrestrial intent. Civilizations might send signals designed for immediate comprehension, or they might use complex, multi-layered encoding intended for advanced recipients. The purpose of a signal could range from a simple "we exist" beacon to sophisticated scientific, cultural, or philosophical communication. Understanding intent requires careful analysis of repetition, modulation, and consistency across multiple observations, as well as an awareness of the limitations imposed by interstellar distance and time delays. Another dimension of interpretation is cross-disciplinary collaboration. Linguists, mathematicians, computer scientists, physicists, and philosophers all contribute insights that may aid in decoding extraterrestrial messages. Understanding a signal may require a holistic approach, integrating knowledge from diverse fields to recognize patterns, infer meanings, and contextualize information within universal physical and mathematical principles. Collaborative frameworks enhance the likelihood of accurately discerning and interpreting alien communications. Long-term monitoring is vital. Signals may be intermittent or periodic, reflecting the technological or environmental constraints of the transmitting civilization. Continuous observation allows researchers to accumulate data, detect repetitions, and analyze patterns over extended periods. Patience is essential. A signal that appears meaningless at first may reveal structure only after years of careful study. This commitment mirrors the gradual accumulation of knowledge that defines human science, highlighting the persistence required to understand cosmic phenomena. Finally, interpreting potential signals informs not only our understanding of extraterrestrial life, but also our strategic and philosophical response. Confirmation of intelligent life would reshape our conception of the universe, our place within it, and our approach to interstellar ethics and diplomacy. Even ambiguous signals expand the boundaries of human imagination, compelling us to consider the technological, cultural, and philosophical diversity of civilizations that may exist across the stars. In conclusion, the interpretation of extraterrestrial signals is a complex, multi-layered challenge. Verification, pattern analysis, decoding, contextual understanding, and the avoidance of false positives are all essential steps. Advanced tools, interdisciplinary collaboration, and long-term observation are necessary to discern the subtle traces of intelligence amid cosmic noise. Whether signals are direct communications, incidental emissions, or artifacts of interstellar technology, the careful interpretation of potential signals allows humanity to explore one of the most profound questions of existence. Are we truly alone? Or are our stars already whispering secrets that we are only beginning to understand? Imagine a civilization far beyond our solar system, equipped with technology far surpassing our own, scanning the cosmos for signs of life. Could they detect Earth and humanity? The possibility that aliens have already found us is both a thrilling and sobering question. By examining the ways in which Earth's activities emit detectable signals into space, we can begin to assess how visible our civilization might be to distant observers. One of the primary indicators of our presence is electromagnetic emissions. Since the advent of radio and television, Earth has been sending signals outward at the speed of light, creating a growing sphere of detectable activity. These signals, though increasingly diluted with distance, carry unmistakable hallmarks of artificial origin. Narrowband transmissions, structured broadcasts, and patterns in frequency and amplitude could signal to an advanced civilization that intelligent life exists here. Radar and satellite transmissions also contribute to our visibility. High-power radar beams, whether used for planetary mapping, weather monitoring, or tracking near-Earth objects, send concentrated energy into space. Even brief bursts, if detected, could indicate technological sophistication and the presence of a civilization capable of harnessing energy in directed forms. Unlike broad radio signals, these emissions are more focused and could stand out as deliberate actions, rather than random noise. Beyond electromagnetic signals, optical and infrared signatures serve as indicators of our presence. City lights, industrial activity, and heat emissions collectively produce detectable anomalies in the visible and infrared spectrum. From orbit or across light years, a technologically advanced observer might identify these patterns as non-natural, suggesting artificial structures and large-scale energy consumption. Observing Earth's night-side illumination could provide clear evidence that a civilization thrives on its surface. Atmospheric composition is another revealing clue. Human activity has altered Earth's atmosphere in measurable ways. Carbon dioxide, methane, chlorofluorocarbons, CFCs, and other industrial byproducts act as technosignatures. From afar, spectroscopy could detect these chemical anomalies in our atmosphere, providing indirect evidence of technological activity. Such signatures might be particularly noticeable to civilizations with refined observational methods capable of analyzing planetary atmospheres around distant stars. Advanced civilizations might also employ gravitational and orbital monitoring. Artificial satellites, space stations, and other structures modify Earth's gravitational field, albeit subtly. While these changes are minor, highly sensitive instruments could potentially detect them, revealing the presence of an intelligent species capable of manipulating its environment. Orbital mechanics, when analyzed over time, could hint at artificial interventions in natural planetary motion, offering another layer of detectative. The scale and timing of our signals matter as well. Humanity's detectable footprint is relatively recent on a cosmic timeline. Our radio and television broadcasts extend only about a century into space. Interstellar distances mean that a civilization located tens, hundreds, or thousands of light years away may not have received our earliest signals yet. Similarly, any response from such a civilization might take centuries or millennia to arrive. This delay frames our detectability as a dynamic and ongoing process. Influenced by both distance and technological progress, interstellar probes add another dimension to the question. As discussed in previous sections, advanced civilizations may send small, autonomous probes to observe emerging technological species. If Earth falls within the trajectory of such a probe, our activities ranging from electromagnetic emissions to industrial development could be cataloged in real time. Unlike distant signal detection, probes offer localized, detailed observation, potentially allowing aliens to study humanity without direct contact. Furthermore, natural amplifiers could make our presence more obvious. Certain regions, such as major cities or industrial zones, emit concentrated energy in multiple forms: electromagnetic, optical, and thermal. These concentrated outputs may stand out against the background noise of our planet, making it easier for distant observers to identify technological activity. In essence, our civilization's brightest and busiest regions act as beacons, highlighting our presence to anyone capable of observing from afar. It's also important to consider the invisibility factor. Not all human activities are equally detectable. Rural areas, forests, and oceans contribute little to the technosignature. And our most advanced technologies, fiber optic communications, encrypted transmissions, and low-energy devices may leave minimal traces. Thus, an alien civilization might perceive Earth as partially active, with detectable signals concentrated in specific regions, requiring careful monitoring and advanced instruments to discern the full picture. Cultural and mathematical markers might also reveal intelligence. Structured patterns in broadcast signals, repetition of prime numbers, or sequences corresponding to mathematical constants could indicate intentional design. A civilization observing our transmissions might recognize these markers as signs of reasoning, logic, and deliberate communication, further confirming the presence of intelligent life. Finally, the prospect of being detected raises philosophical and ethical questions. If we are already observed, what implications does this have for our understanding of the universe, our sense of security, and our place in the cosmic hierarchy? Awareness of detection challenges us to consider the broader consequences of technological development, environmental impact, and interstellar communication. It also invites reflection on the potential motivations and behaviors of distant observers. Are they benign, indifferent, or possibly cautious and protective? In conclusion, humanity's detectable footprint extends across multiple dimensions: electromagnetic emissions, optical and infrared signatures, atmospheric anomalies, orbital changes, and concentrated regional activity. These indicators, collectively, form a rich technosignature that could be recognized by civilizations with advanced observational capabilities. While the vastness of space and the limitations of light-speed communication complicate immediate detection, the possibility that aliens have already found us remains scientifically plausible. By understanding how our presence manifests to distant observers, we gain insight not only into our detectability, but also into our own civilization's technological and cultural evolution, highlighting the profound interplay between observation and existence in the cosmic arena. If Earth has indeed been detected by extraterrestrial civilizations, a natural question arises: how might they respond to our presence? The potential reactions of advanced civilizations depend on their technological capabilities, motivations, ethical frameworks, and strategies for interacting with less developed species. By exploring plausible responses, we can better understand the potential dynamics of interstellar observation and communication. One of the simplest forms of response is passive observation. Just as humans study wildlife without interfering, an advanced civilization may choose to monitor Earth without making contact. This approach minimizes risk and allows observers to gather data on our technological progress, societal structures, and environmental impact. Such surveillance could be conducted via interstellar probes, long-range telescopes, or even subtle manipulation of cosmic signals to observe our reactions. Passive observation ensures that any intervention occurs only when deemed necessary or safe by the observing civilization. Another potential strategy is active monitoring through indirect signals. Aliens might influence our environment or broadcast subtle signals designed to test our awareness and response. This could include modulating naturally occurring cosmic phenomena, sending targeted pulses to specific regions, or creating detectable patterns in interstellar space. These methods allow a civilization to gauge our technological sophistication, critical thinking, and scientific progress without direct interaction. By interpreting these signals, we could gain indirect insights into the presence of advanced observers. Direct communication represents a more assertive response, although it carries risks for both parties. If a civilization decides we are ready for contact, they might send messages encoded in electromagnetic waves, optical pulses, or other high-intensity signals. Such communications could range from simple acknowledgments of our existence to detailed instructions, scientific data, or even philosophical concepts. The timing, frequency, and content of these messages would likely reflect careful consideration, balancing the need to communicate with the potential consequences. of revealing their presence. Some theories propose non-interference policies, often referred to as a cosmic prime directive. Under this approach, aliens intentionally avoid direct contact to allow emerging civilizations to develop independently. Non-interference minimizes the risk of cultural disruption, technological shock, or unintended harm. Earth may be treated as a protected or monitored environment, observed closely but shielded from direct manipulation. This perspective suggests that advanced civilizations could be aware of humanity while deliberately refraining from interaction. Strategic, observation, and risk assessment are also likely priorities. Advanced civilizations may evaluate our potential as allies, competitors, or threats. They could analyze our energy consumption, military capabilities, and technological trends to determine whether interaction is safe or beneficial. The evaluation might involve long-term monitoring, assessment of global cooperation, and tracking of space-based activities, ensuring that any response aligns with their broader interstellar strategy. Interstellar diplomacy could play a role in hypothetical responses. If contact is deemed appropriate, messages might include offers of knowledge exchange, invitations to join interstellar networks, or warnings about environmental stewardship and technological risks. Such communications would require careful design to ensure clarity across linguistic, cognitive, and cultural differences. Advanced civilizations would likely anticipate misinterpretation and implement redundancy, universality, and error-checking mechanisms in their messaging. Some theorists speculate about covert manipulation or guidance. Aliens might subtly influence our development through technological seeding, scientific hints, or even indirect interventions that shape our trajectory without overt contact. This approach could accelerate our progress or prevent self-destruction, all while maintaining plausible deniability. Such strategies assume patience and foresight, with the understanding that long-term outcomes are more important than immediate interaction. The scale of response is influenced by technological disparity. Civilizations millions of years ahead could operate in ways entirely incomprehensible to us, using observational methods or communication channels beyond our current physics. They might monitor quantum-level processes, manipulate gravitational fields, or encode information in exotic forms of matter or energy. For us, their presence could remain virtually undetectable, revealing only subtle anomalies or unexplained phenomena. Ethical considerations likely guide responses as well. Advanced civilizations may adhere to principles of stewardship, responsibility, or respect for emerging life. Their decisions could balance curiosity with caution, ensuring that interference does not endanger developing civilizations. This ethical lens might explain why, despite detecting Earth, no overt contact has occurred, or why enigmatic phenomena, like unexplained interstellar objects, remain subtle and ambiguous. Observation through interstellar probes is another plausible scenario. Small autonomous probes could survey our planet, cataloging information on electromagnetic emissions, technological artifacts, and societal behavior. Such probes may operate stealthily, minimizing detection risk while transmitting data back to their origin civilization. The fleeting passage of Oumuamua, for example, has fueled speculation that interstellar objects could serve as observation platforms, though evidence remains inconclusive. Finally, the diversity of potential responses highlights the complexity of interstellar relations. Some civilizations may ignore us entirely, others may passively observe, and still others may engage subtly or overtly depending on their values, capabilities, and strategic goals. Predicting their behavior requires careful consideration of technological potential, ethical norms, and the long-term perspective inherent to civilizations capable of interstellar travel. In conclusion, if aliens have found us, their responses could range from passive observation to covert guidance, indirect signaling, or direct communication. Strategies may be informed by risk assessment, ethical principles, technological disparity, and long-term objectives. By contemplating these possibilities, we gain insight into not only the challenges of interstellar interaction, but also the profound implications of being a detectable civilization in a vast, complex cosmos. The awareness that we could be observed underscores both our vulnerability and our significance, inviting reflection on our responsibilities as an emerging technological species. The possibility that extraterrestrial civilizations may have already detected Earth raises profound questions about how humanity should prepare for potential contact. While the timing, form, and nature of such contact remain uncertain, thoughtful preparation can help maximize safety, understanding, and opportunity, ensuring that humanity responds wisely to one of the most transformative events imaginable. The first step in preparation is scientific readiness. Humanity must continue to refine the tools and methods used to detect and interpret extraterrestrial signals. This includes expanding radio and optical observatories, developing sensitive detection algorithms, and maintaining long-term monitoring of the cosmos. Accurate observation allows us to recognize potential signals promptly, assess their origin, and determine whether they represent communication, observation, or natural phenomena. By investing in scientific infrastructure, we increase our capacity to respond knowledgeably and responsibly. International collaboration is critical. Contact with an extraterrestrial civilization is not solely a national or regional issue. It is a matter that affects all of humanity. Coordination among space agencies, scientific organizations, and governments ensures that decisions are made transparently and ethically. Collaborative frameworks, such as the International Academy of Astronautics SETI protocols, provide guidelines for responding to signals, sharing information, and avoiding unilateral actions that could endanger or misrepresent humanity. Another key aspect is risk assessment. Contact could range from benign communication to potentially hazardous interaction. Scientists and policymakers must consider the full spectrum of possibilities. Are the visitors benevolent, indifferent, or hostile? Could our response reveal vulnerabilities or invite interference? Preparing for contact requires scenario planning, including contingency strategies for signals, probes, or unexpected encounters. Risk assessment helps humanity avoid panic, miscommunication, and potentially dangerous actions. Communication strategy is equally important. If a signal or message is received, the content, timing, and method of our response must be carefully considered. Messages should be designed to minimize misunderstanding, avoid unnecessary disclosure of sensitive information, and maximize clarity across cognitive and technological divides. Some protocols suggest beginning with simple, universal concepts such as mathematics or physics, to establish a common language before progressing to more complex ideas. By planning communication in advance, we increase the likelihood of meaningful dialogue. Public education and awareness form another pillar of preparedness. Humanity's response to extraterrestrial contact will be influenced by social perception, cultural values, and public reaction. Education initiatives that convey scientific principles, the nature of potential contact, and the uncertainties involved help cultivate rational, informed discourse. Transparency about the possibilities, risks, and procedures can reduce fear and promote collective understanding, ensuring that the public is both informed and engaged. Ethical frameworks guide decision-making. Any response to contact must consider the moral implications of revealing information, making contact, or taking action that affects not only humanity, but potentially other civilizations. Ethical questions include: do we have the right to respond on behalf of all humans? Should we attempt communication if the consequences are uncertain? What responsibilities do we have to preserve life, culture, and knowledge? Addressing these questions in advance provides a foundation for principled decision-making during unprecedented events. Technological preparedness is also essential. Humanity must assess and, if possible, advanced technologies related to communication, defense, and observation. While defensive measures are speculative given the unknown capabilities of an advanced civilization, understanding our technological strengths and limitations allows for informed planning. In parallel, enhancing detection, analysis, and communication systems increases our capacity to engage with extraterrestrial signals. Constructively talk scenario planning offers a structured way to anticipate potential developments. This includes best case, moderate, and worst case scenarios, ranging from receiving simple messages to encountering probes or observing interstellar objects with inexplicable behavior. By considering multiple outcomes, humanity can develop flexible response strategies, reducing uncertainty and increasing resilience. Scenario planning also helps identify knowledge gaps, guiding future research priorities in astrobiology, astrophysics, and communication science. Cultural and philosophical preparation is equally significant. The realization that intelligent life exists beyond Earth challenges fundamental assumptions about our place in the universe. Societies may grapple with questions of identity, meaning, and existential significance. Preparing culturally involves encouraging reflection, dialogue, and philosophical inquiry to help humanity integrate this potential knowledge into worldviews, ethics, and long-term planning. Coordination with existing extraterrestrial research programs is practical and strategic. SETI-METI and space observatories already operate protocols for monitoring, analyzing, and responding to potential extraterrestrial activity. Strengthening these programs, sharing data internationally, and maintaining readiness protocols ensures that any detection is treated with rigor, transparency, and scientific integrity. Collaboration with established initiatives increases efficiency and reduces duplication of effort, enhancing humanity's overall preparedness. Finally, psychological and societal resilience is critical. The discovery that we are observed or that communication is possible may induce fear, excitement, confusion, or skepticism. Preparing societies to handle these reactions requires strategies for stress management, public communication, and fostering rational decision-making. Encouraging resilience ensures that humanity can respond cohesively, avoiding panic, misinformation, or harmful collective behavior. In conclusion, preparing for potential contact with extraterrestrial civilizations requires an integrated approach: scientific readiness, international collaboration, risk assessment, communication planning, ethical consideration, technological preparedness, scenario planning, cultural reflection, coordination with research programs, and societal resilience. While the timing and nature of contact remain uncertain, proactive preparation positions humanity to respond wisely, safeguarding both our species and our future in the cosmos. Whether contact is imminent or centuries away, cultivating awareness, capability, and thoughtful strategy ensures that we are ready to engage with the profound mystery of intelligent life beyond Earth. The search for extraterrestrial life often begins close to home, within our own solar system. While Earth remains the only confirmed cradle of life, the moons, planets, and smaller bodies surrounding our Sun offer intriguing possibilities. Detecting life, or even the potential for life, requires careful observation, advanced technology, and a deep understanding of the conditions that make life possible. One of the most compelling targets is Mars, a planet that has long fascinated scientists and the public alike. Evidence of ancient water flows, dried riverbeds, and polar ice caps suggest that Mars once had conditions potentially suitable for life. Missions, such as NASA's Perseverance rover and ESA's ExoMars program, are focused on searching for biosignatures, chemical or structural evidence of past or present life. Methane emissions, for example, have been detected intermittently in the Martian atmosphere. While these could be produced by geological processes, biological activity remains a tantalizing possibility. Beyond Mars, Several icy moons of the outer planets are promising candidates. Jupiter's moon Europa is thought to harbor a vast subsurface ocean beneath its frozen crust. Tidal forces from Jupiter's immense gravity generate heat, potentially allowing liquid water to exist despite the frigid environment. The presence of water, energy sources, and complex chemistry makes Europa a prime candidate for hosting microbial or even more complex life forms. Future missions, such as NASA's Europa Clipper, aim to probe the ice shell, analyze surface chemistry, and assess the moon's habitability. Saturn's moon Enceladus is another intriguing target. Geysers of water vapor and organic molecules erupt from its south pole, suggesting a subsurface ocean that interacts with a rocky core. These plumes provide a natural window into the ocean below, allowing spacecraft to sample material directly without drilling. The discovery of molecular hydrogen within the plumes hints at the potential for chemical energy sources that could sustain microbial life, making Enceladus an exceptionally compelling destination for astrobiological exploration. Other moons, such as Titan, Saturn's largest satellite, also present fascinating possibilities. Titan has a thick atmosphere, rich in organic compounds and lakes of liquid methane and ethane on its surface. While the chemistry is vastly different from Earth, some scientists speculate that exotic forms of life could exist, utilizing hydrocarbons in place of water. Studying Titan's environment challenges our traditional assumptions about the chemical basis for life, broadening the scope of the search beyond Earth-like conditions. Even small bodies such as asteroids and comets may harbor clues. The discovery of organic molecules in comets, as well as the possibility of water ice within asteroids, suggests that the building blocks of life are widespread in the solar system. Missions like ESAS Rosetta, which studied comet 67P Churyumov-Gerasimenko, have provided valuable insights into the chemistry of these primordial bodies. Some researchers even hypothesize that impacts from comets and asteroids may have delivered essential organic compounds to early Earth, seeding the planet with the ingredients for life. Detection methods in the solar system combine remote sensing, in situ analysis, and laboratory experiments. Orbiters and landers can examine surface chemistry, detect water or organics, and measure atmospheric composition. Spectroscopy allows scientists to identify chemical signatures from orbit, while advanced imaging techniques reveal structural features that may indicate biological activity. In situ experiments, such as analyzing soil samples or testing for metabolic processes, are critical to distinguishing biological signals from purely chemical or geological phenomena. Subsurface exploration is increasingly important. Life may exist in protected environments below harsh surface conditions. Ice-penetrating radar, subsurface drilling, and melting probes are being developed to access these hidden ecosystems. By studying subsurface environments, scientists hope to uncover habitats shielded from radiation, extreme temperatures, and other challenges that might preclude life on the surface. These environments may preserve evidence of past life, or even host extant organisms. Extreme environments on Earth provide models for what to expect elsewhere. Microbial life thrives in deep oceans, acidic lakes, hydrothermal vents, and arid deserts. Studying extremophiles helps astrobiologists understand the range of conditions compatible with life. By identifying chemical and environmental markers in these analogs, scientists develop criteria for detecting life on Mars, Europa, Enceladus, Titan, and other locations. These studies also refine the instruments and methods used in planetary exploration, ensuring that subtle biosignatures are not overlooked. Interdisciplinary collaboration is key to solar system exploration. Geologists, chemists, biologists, planetary scientists, and engineers all contribute expertise. Understanding the potential for life requires synthesizing knowledge about planetary formation, chemical processes, energy availability, and environmental stability. By combining disciplines, researchers can assess habitability more accurately and design missions capable of detecting even the faintest signs of life. Finally, the philosophical and societal implications of discovering life within our solar system are profound. Finding even microbial life elsewhere would confirm that life is not unique to Earth, reshaping our understanding of biology, evolution, and our place in the cosmos. It would also raise ethical questions about planetary protection, the rights of extraterrestrial organisms, and humanity's responsibility in exploring and potentially altering these environments. In conclusion, the search for life within our solar system focuses on planets, moons, and small bodies with water, organic compounds, and energy sources. Mars, Europa, Enceladus, and Titan stand out as the most promising candidates, while asteroids and comets offer insights into the chemical origins of life. Detection methods include remote sensing, in situ analysis, and subsurface exploration, informed by studies of Earth's extreme environments. By combining scientific rigor, technological innovation, and interdisciplinary collaboration, humanity takes the first steps toward answering one of the most profound questions of existence. Are we alone in the solar system? Or is life a common phenomenon across the cosmos? While the solar system offers tantalizing possibilities for life, the vast majority of potential habitats lie beyond our immediate cosmic neighborhood. The search for extraterrestrial life extends to distant star systems, where planets orbiting other stars, known as exoplanets, may harbor conditions suitable for life. Over the past few decades, astronomers have discovered thousands of these worlds, revealing a remarkable diversity of planetary environments and expanding the scope of our search. The first step in this search is identifying planets within the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where temperatures allow liquid water to exist on a planet's surface. Too close, and water evaporates. Too far, and it freezes. Earth resides comfortably within the Sun's habitable zone, providing a template for identifying potentially life-supporting exoplanets. Advanced telescopes and space missions now allow astronomers to detect planets in these zones with increasing precision. Transit photometry is one of the primary methods for detecting exoplanets. This technique measures the slight dimming of a star's light as a planet passes in front of it. By analyzing the amount and duration of dimming, scientists can infer a planet's size, orbit, and, sometimes, atmospheric composition. Missions like NASA's Kepler and TESS have used this method to identify thousands of candidates, many of which reside in their stars' habitable zones. Transit photometry has revolutionized our understanding of how common planets and potentially habitable ones are in the galaxy. Another crucial detection method is radial velocity or Doppler spectroscopy. This approach measures the subtle wobble of a star caused by the gravitational pull of orbiting planets. By analyzing the star's spectrum, astronomers can determine the planet's mass, orbit, and even some atmospheric characteristics. Radial velocity complements transit photometry, allowing scientists to confirm planets and refine estimates of their habitability once potentially habitable exoplanets are identified. Atmospheric characterization becomes essential. Spectroscopy enables scientists to detect molecules such as oxygen, methane, carbon dioxide, and water vapor in exoplanet atmospheres. Certain combinations of gases may indicate biological activity, creating what are known as biosignatures. For example, the simultaneous presence of oxygen and methane, which would normally react and neutralize each other, could suggest continuous replenishment by living organisms. Identifying such signatures is a major goal of current and future exoplanet missions. Advanced telescopes play a pivotal role in this endeavor. The James Webb Space Telescope, JWST, for example, can analyze exoplanet atmospheres in unprecedented detail. Upcoming missions, like the European Space Agency's ARIEL and NASA's HabEx, aim to survey hundreds of planets for signs of habitability and life. These instruments will allow us to study distant worlds with a precision once thought impossible, turning theoretical possibilities into observable phenomena. Binary and multiple star systems add complexity and opportunity. Some exoplanets orbit 2 or more stars, creating unique climatic and gravitational conditions. While this complicates habitability assessments, it also increases the diversity of environments where life might emerge. Studying these systems challenges our understanding of planetary formation and expands the potential for discovering life in unconventional habitats. Extremophiles on Earth guide our expectations. Life on other worlds may not resemble earthly organisms. Microbes survive in extreme temperatures, high radiation, acidic environments, and deep underground. This suggests that life elsewhere might exist under conditions previously considered inhospitable, broadening the range of exoplanets considered viable. Planets with subsurface oceans, thick atmospheres, or exotic chemistries may host life forms adapted to their unique environments. The Fermi paradox frames the search with profound questions. Despite the vast number of stars and potentially habitable planets, we have yet to observe direct evidence of extraterrestrial civilizations. This paradox drives much of the scientific and philosophical discourse around life beyond Earth. It raises questions about the rarity of intelligent life, the lifespan of civilizations, and the methods we use to detect them. Searching beyond our solar system addresses both the practical and existential dimensions of this paradox. Interstellar communication also becomes a factor when studying distant worlds. Detecting artificial signals such as radio waves, laser pulses, or other technosignatures could indicate intelligent life. Programs like SETI search for extraterrestrial intelligence, scan the skies for structured signals that deviate from natural astrophysical phenomena. The detection of such signals would revolutionize our understanding of life in the universe, confirming that intelligence has emerged elsewhere. Statistical models and probabilistic reasoning help guide the search. The Drake equation, for example, estimates the number of detectable civilizations in our galaxy by combining factors such as star formation rates, planetary prevalence, habitability, and the emergence of life, while exact values remain uncertain. This framework provides a structured approach to quantifying the likelihood of extraterrestrial life and prioritizing observational targets. Future technologies promise to enhance our search further. Concepts such as space-based interferometers, star shades, and high-contrast imaging may allow direct visualization of Earth-like planets. Missions capable of resolving surface features or detecting seasonal changes could reveal signs of vegetation, oceans, or even industrial activity. Such advancements would bridge the gap between indirect detection and direct observation, bringing us closer to confirming life beyond Earth. Societal and philosophical implications are profound. Discovering life in distant star systems challenges the notion of Earth's uniqueness and reframes our understanding of biology, evolution, and the potential for intelligence elsewhere. Even microbial life would indicate that life emerges readily under suitable conditions, suggesting that the universe teems with possibilities. Intelligent life, if found, would prompt unprecedented considerations regarding ethics, communication, and interstellar coexistence. Finally, the search beyond our solar system is a long-term endeavor, shaped by patience, innovation, and global cooperation. While detection may take decades, centuries, or longer, each discovery refines our understanding of planetary formation, habitability, and the prevalence of life. The quest expands not only our scientific knowledge, but also our imagination, inspiring humanity to envision its place in a galaxy filled with potential neighbors. In conclusion, searching beyond our solar system involves identifying exoplanets in habitable zones, characterizing their atmospheres, and detecting potential biosignatures or technosignatures. Methods such as transit photometry, radio velocity spectroscopy, and advanced telescopes allow increasingly precise observations. Extremophiles, statistical models, and technological innovations broaden the scope of what is considered habitable, while philosophical and societal reflection prepares humanity for the profound implications of discovery. This cosmic exploration brings us closer to answering one of the deepest questions of all. Is life a universal phenomenon, or are we alone in the vast reaches of space? Beyond searching for microbial or biological life, the quest for extraterrestrial intelligence involves identifying technosignatures observable signs of advanced civilizations. While biosignatures reflect the chemical or physical traces of life, technosignatures indicate the presence of technology, infrastructure, or purposeful manipulation of the environment. Detecting such signals requires both sophisticated observation methods and careful interpretation, as natural phenomena can often mimic artificial signatures. One of the most familiar approaches is radio signal detection. Since the mid-20th century, programs like SETI, Search for Extraterrestrial Intelligence, have scanned the skies for electromagnetic emissions that differ from natural astrophysical sources. Narrowband signals, pulse transmissions, or structured patterns could indicate deliberate communication rather than random cosmic noise. The discovery of such signals would suggest that a civilization has developed technology capable of broadcasting beyond its own star system, optical and laser-based. Signals provide another promising avenue. Highly focused laser beams can traverse interstellar distances with minimal energy loss, making them ideal for long-range communication. Astronomers have begun searching for transient optical flashes or continuous beams that could signify intentional messaging. Detecting these technosignatures requires precise timing, large telescopes, and the ability to distinguish artificial signals from natural stellar variability. Megastructures and astroengineering projects offer a more speculative, yet fascinating approach. A Dyson sphere or swarm hypothetical constructs designed to capture a star's energy would produce unusual patterns in a star's light output. Astronomers can search for these anomalies by analyzing stellar brightness and infrared emissions. While no definitive evidence has been found, unexplained fluctuations in starlight, such as those observed around the star KIC 8,462,852, also known as Tabby star, spark curiosity and highlight the potential for detecting large-scale engineering. Exoplanet atmospheric manipulation may also serve as a technosignature. Advanced civilizations could alter their planet's atmospheres for climate control, resource extraction, or even communication purposes. Spectroscopic analysis could reveal gases in unexpected proportions or unnatural combinations, suggesting deliberate modification rather than geological or biological processes. Detecting these anomalies requires careful modeling to differentiate natural from artificial causes. But the potential reward is profound. Evidence of an intelligent species manipulating its environment on a planetary scale. Artificial satellites, megastructures, and probes could act as local technosignatures within a planetary system. Autonomous probes may observe, relay information, or even leave detectable traces. Observations of unusual trajectories, reflected light, or radio emissions from such objects might indicate intentional placement by an intelligent civilization. While these signatures are subtle and often indistinguishable from natural debris without detailed analysis, advances in observation technology could make detection increasingly feasible. Astrophysical anomalies sometimes prompt speculation about intelligent activity. Unexplained phenomena, such as unusual pulsar signals, periodic dimming of stars, or patterns in cosmic background radiation, could indicate purposeful manipulation. While most anomalies are eventually explained through natural processes, the possibility remains that some may represent the footprints of civilizations operating at a scale far beyond current human comprehension. Mathematical and universal constants may serve as bridges for interstellar communication. Advanced civilizations might encode information using universally recognized concepts, such as prime numbers, the hydrogen line, or patterns derived from physical constants. By scanning for signals with these characteristics, scientists aim to identify messages intended for any technologically capable observer. The underlying principle is that mathematics transcends culture, making it a likely medium for interstellar messaging. Artificial light signatures from planetary surfaces are another avenue. Nighttime illumination on exoplanets, detectable via high-resolution imaging or photometry, could indicate cities, industrial areas, or other large-scale human-like activity. While current telescopes cannot resolve surface lights at interstellar distances, future instruments might detect the cumulative effects of artificial illumination on exoplanets, providing indirect evidence of technological civilizations. Interstellar megastructures and energy management could also leave detectable footprints. Civilizations harvesting energy at a stellar scale may emit waste heat, producing infrared signatures distinct from natural planetary or stellar processes. Observatories sensitive to infrared radiation, such as the James Webb Space Telescope, can identify these anomalies, offering potential evidence of energy-intensive technological activity. Data analysis and machine learning are becoming indispensable for detecting technosignatures. The sheer volume of data collected from radio telescopes, space observatories, spectroscopic surveys necessitates automated algorithms capable of identifying patterns and anomalies. Machine learning models can differentiate between natural noise and potential artificial signals, flagging candidates for further investigation. These tools increase both the sensitivity and efficiency of searches for intelligent life. Challenges in technosignature detection remain formidable. False positives, cosmic interference, and natural astrophysical processes can mimic artificial signals. Scientific rigor requires careful verification, repeated observation, and corroboration across independent instruments. Detecting a technosignature is not merely a technical problem. It also involves interpreting intent, distinguishing deliberate from incidental signals, and understanding the context of any potential communication. Philosophical implications are equally profound. The discovery of a technosignature would confirm not only the existence of life, but the presence of intelligence, creativity, and technological sophistication beyond Earth. It would transform our understanding of biology, sociology, and engineering on cosmic scales, raising questions about our future trajectory, potential contact protocols, and our responsibilities in a broader interstellar community. In conclusion, the search for technosignatures complements traditional biosignature investigations, focusing on signs of intelligent life rather than merely biological activity. Methods include detecting radio and optical signals, analyzing atmospheric compositions, searching for megastructures, observing planetary illumination, and interpreting astrophysical anomalies. Advanced data analysis techniques are essential for identifying patterns in vast datasets, while careful verification ensures scientific integrity. Detecting technosignatures represents humanity's quest not just to understand life, but to recognize intelligence beyond our world, offering profound insights into the nature of civilization and our place in the universe. In October 2017, astronomers made a discovery that would captivate the world and ignite debate across the scientific community: the detection of Oumuamua, the first known interstellar object to pass through our solar system. Unlike typical asteroids or comets, Oumuamua exhibited unusual properties that challenged conventional understanding, prompting speculation about its origin and even its potential artificial nature. Oumuamua was initially identified by the Pan-STARRS 1 telescope in Hawaii, its elongated, cigar-like shape immediately drawing attention. Its dimensions, estimated to be roughly 800 meters long and only about 80 meters wide, were unlike any known solar system object. Its reddish hue suggested a surface rich in organic molecules, similar to objects in the outer solar system. But its speed and trajectory clearly marked it as interstellar, originating from beyond the sun's gravitational influence. One of the most puzzling features of Oumuamua was its non-gravitational acceleration. As it traveled through the solar system, it deviated slightly from the path predicted solely by gravity. In typical comets, such behavior is explained by outgassing, the release of gas and dust as ice sublimates, generating a small thrust. However, Oumuamua showed no detectable cometary tail, no water vapor, and no dust emissions large enough to account for the acceleration. This anomaly fueled a wide spectrum of hypotheses, ranging from unusual ice compositions to highly reflective surfaces. Some scientists, most notably Harvard astronomer Avi Loeb, proposed that Oumuamua could be a technological artifact, possibly a light sail sent intentionally by an advanced civilization. Its elongated, thin shape and apparent lack of outgassing seemed consistent with a highly reflective structure capable of harnessing stellar radiation for propulsion. While this idea remains speculative and controversial, it underscores the challenges of interpreting phenomena from objects that are fundamentally different from anything previously observed. The trajectory of Oumuamua offered further intrigue. Traveling at roughly 315,000 kilometers per hour, 196,000 miles per hour, it passed closest to the Sun at a distance of about 0.25 astronomical units and left the solar system on a hyperbolic escape path. Its approach from the direction of the star Vega, part of the Lyra constellation, suggested it had journeyed for millions of years through interstellar space. Such a long voyage implies remarkable durability. Whether it was a natural object like a fragment of a planet or a comet, or an artificial construct engineered to survive the harsh environment between stars, spectral analysis provided additional clues, though they were ambiguous. Observations in the visible and near-infrared range indicated a surface that was reddish, likely due to space weathering and cosmic radiation. No emission lines associated with active outgassing were detected. Reinforcing the puzzle, Oumuamua displayed behavior reminiscent of comets, but lacked the physical evidence. The combination of these anomalies made it one of the most mysterious objects ever observed in human history. Scientists proposed several natural explanations. One suggestion was that Oumuamua could be composed of frozen hydrogen, allowing sublimation without producing a detectable tail. Another hypothesis considered it a fragment of a tidally disrupted planet from another star system. While these models attempt to reconcile its peculiarities, none fully account for its elongated shape, acceleration, and composition simultaneously. The debate continues, illustrating the limits of current knowledge and technology. Observing Oumuamua was an immense challenge due to its rapid transit through the solar system. By the time it was discovered, it was already leaving, providing a short observational window. Multiple telescopes around the world collaborated to gather as much data as possible, measuring brightness, fluctuations, rotation, and trajectory. This effort demonstrated the global scientific community's capacity to respond quickly to transient interstellar events, highlighting both the excitement and the limitations of real-time study. The discovery of Oumuamua prompted broader questions about interstellar visitors. If one such object passed through the solar system in 2017, how many others might have passed unnoticed? Are these objects merely cosmic debris, or do some represent deliberate exploration or probes from advanced civilizations? While natural explanations remain dominant, the very existence of such interstellar objects opens the door to speculation about intelligent life beyond the solar system. The public response to Oumuamua was equally remarkable. Media outlets, documentaries, and social platforms debated the alien probe hypothesis, blending scientific curiosity with imagination. This fascination reflects humanity's enduring desire to connect with the unknown, to find signs that we are not alone in the cosmos. Regardless of its origin, Oumuamua became a cultural and scientific milestone, inspiring a renewed focus on interstellar exploration. From a scientific perspective, Oumuamua also challenged assumptions about planetary formation and interstellar dynamics. Its unusual shape, speed, and composition suggested that planetary systems elsewhere may produce objects radically different from what we observe locally. This insight encourages the study of exoplanetary systems not only for planets themselves, but also for the debris and fragments they eject into the galaxy. Understanding these populations could reveal patterns about the frequency, composition, and trajectories of interstellar visitors. Furthermore, Oumuamua serves as a call to expand observation capabilities. Detecting interstellar objects requires continuous monitoring of the sky with sensitive, wide-field telescopes, capable of identifying faint, fast-moving bodies. Future projects, such as the Vera C. Rubin Observatory, are designed to enhance detection rates, potentially allowing humanity to observe dozens or even hundreds of interstellar objects per year. Each new detection could provide valuable data, refining models and opening new avenues for understanding the galaxy's population of interstellar matter. In conclusion, Oumuamua remains one of the most enigmatic objects ever observed. Its elongated shape, hyperbolic trajectory, and non-gravitational acceleration challenge existing models of natural celestial bodies, prompting speculation about artificial origins. Whether it is a remnant of a distant planetary system, a fragment of cosmic debris, or a deliberate probe from an advanced civilization, Oumuamua exemplifies the profound mysteries of the cosmos. It reminds us that interstellar space is not empty, but filled with potential clues about the existence of life, the diversity of planetary systems, and the extraordinary phenomena awaiting discovery. After the groundbreaking discovery of Oumuamua in 2017, astronomers remained alert to the possibility of other interstellar visitors passing through our solar system. In early 2023, the astronomical community announced another remarkable detection, 3I Atlas. This object, like Oumuamua, originates from beyond the Sun's gravitational domain, entering our solar system on a hyperbolic trajectory. The discovery of 3I Atlas marks the second confirmed interstellar object, highlighting that such visitors may be more common than previously imagined. 3I Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of telescopes designed to monitor near-Earth objects. Unlike Oumuamua, which displayed a highly elongated, cigar-like shape, 3I Atlas appeared to be a more typical comet-like object, with visible outgassing as it approached the inner solar system. Observations revealed that its trajectory, speed, and orbit were consistent with interstellar origins, confirming its status as a genuine visitor from another star system. The significance of 3I Atlas lies not only in its interstellar trajectory, but also in what it can tell us about the diversity of interstellar objects. While Oumuamua sparked speculation due to its peculiar shape and lack of outgassing, 3I Atlas behaves more like familiar solar system comets. Its activity suggests that icy bodies may be ejected from distant planetary systems and travel across interstellar space, carrying clues about the formation and composition of other worlds. By comparing these two objects, scientists can begin to understand the range of properties exhibited by interstellar visitors. Observations of 3I Atlas also contribute to our understanding of planetary system dynamics. The object likely originated from a distant star system, possibly ejected through gravitational interactions with massive planets. Studying its composition and orbit allows astronomers to infer characteristics of its home system, such as the presence of large planets capable of flinging debris into interstellar space. Each interstellar object thus serves as a messenger, carrying information about the processes shaping other planetary systems. The study of 31ATLAs raises intriguing questions about the possibility of artificial origins. Although its cometary behavior is consistent with natural formation, some researchers remain open to alternative interpretations. Could a civilization intentionally launch objects to probe nearby star systems? Are there engineered interstellar artifacts hidden among the natural debris? While these notions are speculative, they remind us that interstellar objects provide a unique opportunity to test the limits of both our imagination and our observational techniques. Recent detections suggest that the frequency of interstellar visitors may be higher than initially believed. Statistical models estimate that objects like Oumuamua and 3I Atlas could pass through the inner solar system every few years. But many likely go undetected due to their small size and high speed. Improving survey capabilities and sky monitoring technologies increases the likelihood of identifying more interstellar objects, allowing scientists to build a more comprehensive picture of the population and properties of these cosmic travelers. The characteristics of 3I ATLAS provide a valuable contrast to Oumuamua. Its visible coma and tail indicate sublimation of volatile compounds, such as water, carbon dioxide, or other ices, which is typical of solar system comets. Its rotation, albedo, and spectral properties are being carefully studied to understand its composition. These observations help scientists determine whether interstellar objects predominantly consist of ices, rocks, or a combination, offering insights into the distribution of materials in distant star system. Spectroscopy of 3I ATLAs has revealed the presence of complex organic molecules, hinting that the building blocks of life may be widespread throughout the galaxy. Just as comets in our solar system are thought to have contributed to the emergence of life on Earth, interstellar comets may carry prebiotic compounds between star systems, acting as cosmic delivery mechanisms. This interstellar seeding concept suggests that the ingredients for life may be more common than the occurrence of life itself. Another recent candidate, C 2019 Q for Borisov, further emphasizes the diversity of interstellar visitors. Discovered in 2019, Borisov was clearly cometary, exhibiting substantial outgassing and a more conventional shape compared to Oumuamua. Its chemical composition resembled that of solar system comets, including water, carbon monoxide, and cyanide compounds. Borisov reinforced the notion that interstellar space may be populated with a variety of icy bodies ejected from distant systems, each carrying information about its origin. The trajectory and velocity analysis of these objects reveals a common pattern. They enter the solar system at high speeds, often traveling tens of kilometers per second relative to the Sun. Their hyperbolic orbits confirm that they are not gravitationally bound, making them true visitors rather than long-term members of our planetary neighborhood. These dynamics also imply that interstellar objects may traverse vast distances, enduring millions or even billions of years in cold, empty space before encountering a new solar system. Could these visitors be deliberately seeking Earth? This question captures both public imagination and scientific curiosity, while the overwhelming majority of evidence points to natural origins. Researchers like Avi Loeb and others have suggested that advanced civilizations might deploy probes for exploration or observation. Objects such as Oumuamua, with its unusual shape and trajectory, spark debate about the potential for interstellar reconnaissance or passive observation of other worlds, even if unlikely. Considering this possibility encourages careful observation and analysis of anomalous objects. The detection of interstellar objects is also transforming observational astronomy. Telescopes worldwide now conduct continuous surveys to identify fast-moving objects, refine orbital calculations, and measure compositional properties. Projects like Pan-STARRS, Atlas, and the Vera C. Rubin Observatory enhance our ability to detect smaller and more distant interstellar visitors, potentially uncovering hundreds of previously unknown objects each year. Each new discovery expands the dataset, helping scientists understand the population statistics, formation mechanisms, and potential for life-bearing compounds. The study of 3I Atlas and similar objects has implications for astrobiology. If interstellar objects regularly carry water, organics, and other prebiotic materials, they may serve as natural vehicles for distributing the ingredients of life throughout the galaxy. Even without intelligent intervention, these objects could facilitate a cosmic genealogy of life, delivering essential molecules across vast distances and potentially increasing the likelihood of life emerging on habitable planets. Finally, the cultural and philosophical impact of interstellar objects cannot be understated. Each discovery challenges humanity's perception of the universe as a static, isolated environment. The realization that other star systems send debris and potentially more complex objects into our solar system sparks wonder and speculation. Whether natural or artificial, these cosmic visitors remind us that the galaxy is dynamic, interconnected, and full of mysteries waiting to be explored. In conclusion, 31ATLAS, along with Oumuamua and Borisov, demonstrates that interstellar objects are not rare anomalies, but part of a broader cosmic phenomenon. Their diverse properties, from comet-like activity to enigmatic shapes, offer valuable insights into the composition and dynamics of other planetary systems. While the majority of evidence supports natural origins, the possibility of artificial interstellar probes cannot be entirely dismissed, encouraging careful observation and analysis. Each interstellar visitor carries the potential to inform us about the galaxy, the distribution of life's building blocks, and, perhaps, the presence of advanced civilizations beyond our solar system. With the discoveries of Oumuamua, 3I Atlas, and other interstellar visitors, a natural and fascinating question arises. Could advanced extraterrestrial civilizations have detected Earth? While this question straddles the line between science and speculation, it is grounded in observable phenomena, physics, and a growing understanding of what it would take to track a planet like ours from the vast distances of space. One key factor is Earth's electromagnetic footprint. Since the early 20th century, humanity has been emitting a range of radio, television, and radar signals into space. These signals, traveling at the speed of light, have now reached distances of over 100 light-years. An advanced civilization with sensitive enough instruments could detect these emissions, interpret them as artificial, and infer the presence of a technologically active planet. Signals like radar pings, broadcast television, or even the early transmissions of analog radio could serve as unmistakable markers of intelligent life. Beyond electromagnetic emissions, interstellar objects themselves could act as messengers. If an advanced civilization were aware of the presence of other planetary systems, it might deploy probes or sensors to gather data. Oumuamua and 3I Atlas, while most likely natural, highlight the feasibility of small objects traversing interstellar space undetected until they approach a system. If intelligent civilizations employ similar strategies, probes could observe Earth from a safe distance without revealing themselves directly. These hypothetical probes could collect information about our atmosphere, electromagnetic emissions, or even artificial lights on the night side of our planet. Observing planetary atmospheres provides another avenue for detection. From a distance, Earth reveals its unique chemical signature, notably oxygen and methane, in quantities that are out of equilibrium. These gases are strong biosignatures, indicating the presence of life. Advanced observers could also detect industrial pollutants, such as chlorofluorocarbons, CFCs, which are entirely artificial and suggest technological activity. By combining these atmospheric markers with observations of surface features, A civilization might conclude that Earth hosts both life and intelligence. The timing of interstellar travel also plays a crucial role. Many stars with habitable zones lie tens or hundreds of light-years away. Any probe or signal sent from these systems would require decades, centuries, or millennia to reach Earth. Consequently, any civilization capable of detecting our electromagnetic emissions must also possess extremely patient, long-term planning abilities. While this may seem implausible, the vast timescales of the galaxy render even extremely slow reconnaissance efforts meaningful. Natural. Interstellar objects could serve as passive observers or markers. A civilization could place a small sensor or reflective array on a comet or asteroid, allowing it to drift through space while continuously monitoring planetary systems it encounters. The principle is similar to the Voyager probes, which carry information about Earth but travel largely autonomously. Detecting such objects would require extraordinary sensitivity and the ability to distinguish artificial components from natural rock and ice. Advanced technological capabilities would also shape the ability to track. Earth highly developed civilizations might use gravitational lensing, neutrino detection, or quantum communication methods to observe distant systems with unprecedented resolution. Such methods could allow indirect monitoring of planetary environments, capturing data on atmospheric composition, surface changes, or even signs of industrial activity. These approaches highlight that detection is not necessarily limited to direct visits. Passive observation from afar is both feasible and efficient for advanced civilizations. The role of interstellar travel further complicates the question. Suppose a civilization intentionally sends probes to explore distant systems. In that case, these probes might be designed to remain undetectable, entering solar systems with minimal disturbance to avoid alerting native species. This stealth strategy would explain why no confirmed alien artifacts have been observed, while leaving open the possibility that we are being monitored discreetly. Interstellar visitors like Oumuamua spark curiosity because they demonstrate that high-speed transit between stars is physically possible, even if naturally occurring. Hypothetical indicators of observation could include anomalous interstellar trajectories or unexpected non-gravitational accelerations, such as those observed in Oumuamua. While natural explanations exist, these anomalies inspire questions about intentional manipulation. Could a civilization adjust a probe's course for optimal observation? Could reflective surfaces be used to harness solar radiation for propulsion? These questions underscore the subtle line between natural phenomena and potential artificial intervention. Exoplanet studies provide context as well. If other civilizations monitor planetary systems, they likely focus on planets' inhabitable zones with biosignature gases or surface indicators of water and life. Earth's combination of liquid water, atmospheric composition, and technological emissions makes it a prime candidate for detection. From a galactic perspective, Earth's uniqueness is not absolute, but its signals and biosignatures create a relatively distinct pattern that could attract attention. The Fermi paradox frames these considerations with profound implications. If intelligent life is common, why have we not yet detected clear evidence of observation? One possibility is the immense scale of the galaxy. Even a civilization monitoring nearby stars would have enormous distances and time delays to contend with. Another is deliberate avoidance, sometimes called the zoo hypothesis, suggesting advanced civilizations may observe without direct contact to allow emerging civilizations like ours to develop naturally. Technosignatures and indirect detection extend this discussion. Beyond radio signals, potential indicators include megastructures, atmospheric manipulation, or laser emissions detectable across interstellar distances. Any of these signs could alert extraterrestrial observers to our presence, even without sending physical probes. Future surveys and space-based telescopes will enhance our ability to detect similar technosignatures in other systems. helping to frame our own detectability in a cosmic context. Cultural and psychological dimensions also matter. The idea that aliens may have tracked Earth raises both excitement and caution. It challenges anthropocentric views and encourages reflection on how humanity presents itself to the cosmos. If we are observable, what do our signals say about our civilization? Are we sending inadvertent messages about our values, conflicts, and technology? These questions are as much about introspection as they are about astrophysics. Future detection strategies may shift the balance. As our observational capabilities improve, we may identify objects or phenomena suggesting that interstellar reconnaissance is possible. Deep sky surveys, precise spectroscopy, and long-term monitoring could uncover anomalies in our solar system consistent with distant observation. Even absent definitive evidence, preparing for such possibilities encourages scientific rigor, innovation, and philosophical reflection. In conclusion, while there is no direct evidence that aliens have tracked Earth, multiple avenues suggest it is plausible. Electromagnetic emissions, atmospheric signatures, interstellar probes, and natural cosmic phenomena all provide potential means for distant civilizations to observe our planet. The discoveries of Oumuamua, 3I ATLAS, and Borisov demonstrate that interstellar travel is feasible, even if natural, and raise the question of whether deliberate observation could occur. Advanced technologies, patient planning, and stealth strategies make the detection of civilizations both subtle and challenging. Ultimately, contemplating these possibilities expands our understanding of Earth's place in the galaxy, highlighting both our vulnerability and our potential significance in the cosmic network of life. Since the mid-20th century, humanity has embarked on one of the most profound and ambitious endeavors in history: the search for intelligent extraterrestrial life. This quest, often abbreviated as SETI search for extraterrestrial intelligence, relies on the principle that advanced civilizations may broadcast signals, either intentionally or unintentionally, into space. By listening carefully to the cosmos, we hope to detect these signals and answer one of humanity's most enduring questions: are we alone? The earliest SETI initiatives emerged with the advent of powerful radio telescopes, capable of detecting faint signals from distant stars. Pioneers like Frank Drake, with his famous Drake equation, formalized the scientific approach, estimating the probability of communicative civilizations in the Milky Way. While the equation includes numerous uncertainties, such as the fraction of habitable planets that develop life or intelligence, it established a framework for systematic exploration. Listening to the cosmos involves scanning a broad range of electromagnetic frequencies, from radio waves to optical signals. Radio waves are particularly appealing because they travel vast distances with minimal interference from interstellar matter. By targeting regions of space near stars with potentially habitable planets, SETI programs aim to identify anomalous signals that cannot be explained by natural astrophysical processes. Such signals could be narrowband transmissions, repeated pulses, or patterns indicative of intelligence. One of the first major SETI experiments, Project Ozma in 1960, targeted nearby sun-like stars using a radio telescope in Green Bank, West Virginia. Although it did not detect extraterrestrial transmissions, it proved that systematic searches were feasible. Over the following decades, technological improvements enabled more sensitive and comprehensive surveys. Modern observatories such as the Allen Telescope Array continuously monitor hundreds of thousands of stars, seeking faint signals that might originate from distant civilizations. The challenge of signal detection is immense. Cosmic noise, terrestrial interference, and the sheer distances involved make identifying intentional transmissions extraordinarily difficult. Signals weaken as they travel, often becoming indistinguishable from background radiation. Scientists employ sophisticated algorithms and data analysis techniques to sift through vast quantities of information. searching for patterns, repetitions, or anomalies that could indicate an intelligent source. Another approach involves optical SETI, which seeks brief, high-intensity light pulses like lasers that could function as interstellar beacons. A civilization aiming to announce its presence might favor laser pulses over continuous radio signals due to their energy, efficiency, and detectability across vast distances. Observatories equipped with photodetectors and fast electronics scan nearby stars for such transient flashes, analyzing their timing, intensity, and frequency to distinguish potential artificial origins from natural phenomena, like cosmic rays or stellar flares. The Fermi paradox remains central to this search. Despite decades of listening, humanity has yet to receive a confirmed signal from intelligent life. This apparent silence has prompted various hypotheses. Perhaps civilizations are exceedingly rare, or technological societies have short lifespans relative to cosmic timescales. Another possibility is that advanced civilizations deliberately avoid broadcasting to prevent detection, a concept sometimes referred to as the dark forest hypothesis. Yet the absence of evidence is not evidence of absence. Our observational window is limited, and the galaxy is vast. Technosignatures, a term that encompasses any observable effect of technology, have become a key focus of modern searches. Unlike the early focus on narrowband radio signals, technosignatures include megastructures, industrial pollutants, or patterns in stellar light that indicate artificial modification. For example, a civilization might build large solar arrays or Dyson-like structures around its star to capture energy. These constructs could produce detectable anomalies in a star's brightness or spectrum, offering indirect evidence of advanced intelligence. Recent efforts have leveraged massive data analysis techniques and global collaboration. Projects like Breakthrough Listen, funded by private initiatives, aim to scan the entire sky for unusual signals, recording petabytes of data for later analysis. These searches include both nearby stars and distant galaxies, recognizing that even civilizations millions of light-years away could, in principle, transmit signals detectable by sufficiently sensitive instruments. The integration of machine learning allows astronomers to detect subtle patterns and reduce false positives. Enhancing the likelihood of discovery, historical anomalies provide further motivation. Occasionally, unusual signals such as the famous WOW signal detected in 1977 have sparked excitement due to their unexplained characteristics. While many of these anomalies are eventually attributed to natural or terrestrial sources, they serve as reminders of the possibility that intelligible, extraterrestrial transmissions could appear in unexpected ways. Each anomaly drives refinement in detection methods, ensuring that humanity remains vigilant and responsive. Beyond passive listening, some propose active SETI or messaging extraterrestrial intelligence, in which humanity deliberately broadcasts signals into space. These messages range from binary code to musical compositions, aiming to introduce our presence to unknown civilizations. Active efforts are controversial as they raise questions about potential risks, cultural implications, and whether humanity has the authority to announce itself on behalf of the planet. Nevertheless, they reflect our desire not only to search, but also to communicate with intelligent life. The role of interstellar objects like Oumuamua and ITLAS intersects with signal searches. While these objects are likely natural, their trajectories through the solar system demonstrate that physical probes could complement radio or optical searches. If extraterrestrial civilizations deploy autonomous probes, these visitors could observe Earth passively, potentially transmitting data across interstellar distances or subtly interacting with their environment. Monitoring for such objects adds another dimension to SETI, blending observational astronomy with speculative scenarios. Philosophical implications of signal searches are profound. Detecting extraterrestrial life would reshape our understanding of biology, technology, and civilization. It would challenge anthropocentric assumptions, forcing humanity to consider its place within a vast, interconnected cosmos. Even the absence of signals carries meaning, informing models of planetary habitability, the prevalence of intelligent life, and the potential longevity of technological civilizations. In conclusion, listening to the cosmos is a delicate, meticulous, and patient endeavor. Humanity continues to scan the heavens with ever-increasing precision, hoping to capture faint whispers from distant civilizations. Through radio waves, laser pulses, technosignatures, and interstellar observations, we expand the boundaries of knowledge, probing the silent vastness for signs of others who may be looking back at us. Each effort, whether it yields a signal or reinforces silence, deepens our understanding of the universe and strengthens the quest to answer the ultimate question: are we alone? Or are we part of a greater galactic community? Imagine receiving a signal from the depths of space, a faint whisper carried across light years of emptiness. What would it mean? How could we possibly understand it? The prospect of decoding alien messages is both thrilling and profoundly challenging, blending the disciplines of linguistics, mathematics, computer science, and astrophysics. One of the first considerations is signal identification. Before decoding, scientists must determine whether a detected signal is indeed artificial. Natural cosmic phenomena, pulsars, quasars, stellar flares, and cosmic background radiation produce a vast array of complex signals. An artificial signal would likely exhibit regularity, repetition, or patterns that cannot be explained by natural processes. Narrow bandwidth radio transmissions, precisely timed pulses, or non-random sequences are primary indicators of intelligent origin. Mathematics as a universal language is central to decoding efforts. Since physical laws are consistent throughout the cosmos, mathematical concepts may serve as a bridge between species. Prime numbers, the Fibonacci sequence, or simple geometric ratios could be embedded in a signal as a form of introduction or test of intelligence. For example, sending a sequence of prime numbers as pulses or binary patterns could demonstrate intentionality and reasoning, effectively saying, "We exist and we are intelligent." Binary coding is another potential approach. Binary signals composed of ones and zeros are simple, robust, and relatively immune to interstellar noise. Binary representations can encode numbers, text, or images. Early conceptualizations of alien messages, such as the Arecibo message of 1974, relied on a binary grid to convey fundamental information: numbers, chemical elements, DNA structure, a human figure, and our solar system. This type of communication assumes that mathematics and basic chemistry are universally understood, allowing the recipient to interpret the message without shared language or culture. Visual encoding could accompany or replace radio pulses. Two-dimensional images or patterns can represent concepts visually, such as the periodic table or molecular structures. By arranging binary sequences into grids, aliens might convey pictures that illustrate fundamental aspects of their biology, technology, or environment. Decoding such images requires recognizing the intentional structure, dimensions, and conventions used to organize the data process that may be intuitive for some concepts and extraordinarily difficult for others. Time-based encoding offers additional possibilities. Signals could rely on precise timing, pulsation intervals, or rhythmic patterns to convey information. The WOW signal detected in 1977 exemplifies the intrigue of timing-based anomalies, though it remains unexplained. Temporal patterns could encode numbers, letters, or symbols through duration, spacing, or repetition. Interpreting these patterns demands careful statistical analysis to distinguish intentional structure from random fluctuation or natural. Astrophysical events, compression, and redundancy are essential for practical interstellar messaging. Signals traveling across light years weaken and degrade, potentially losing information. Intelligent civilizations might employ redundancy to ensure their message survives transit, repeating sequences or encoding information multiple times. Compression algorithms could reduce signal length while preserving essential meaning, similar to modern data transmission methods. Recognizing patterns and redundancy could be a crucial first step in decoding alien communication. Language complexity is a formidable challenge. Even with successful detection, interpreting syntax, semantics, or cultural context may be nearly impossible. Unlike human languages, which rely on shared sensory experiences and cultural knowledge, an alien language might encode concepts entirely foreign to human thought. Researchers may need to focus on symbolic universals, such as mathematical constants, physics, or universal chemistry, to establish a common foundation before attempting to understand more abstract ideas. Machine learning and AI have become invaluable tools in decoding efforts. Algorithms can identify patterns, detect anomalies, and simulate possible interpretations faster than human cognition. By analyzing vast datasets of candidate signals, AI can propose hypotheses about meaning, organization, or purpose, even when the underlying system is unfamiliar. Machine learning can also test hypothetical decoding schemes against statistical models, reducing the risk of misinterpretation and guiding human researchers toward promising leads. Ethical considerations play a role as well. Before attempting to reply, humanity must consider potential consequences. A message may contain knowledge that could benefit civilization or, alternatively, information that could pose risks. While speculation abounds about hostile intentions, most scientific discourse emphasizes caution, patience, and verification. Decisions about responding to alien signals involve not just science, but global policy, philosophy, and diplomacy. Historical thought experiments provide insights into possible strategies. Scientists like Carl Sagan and Stephen Hawking explored scenarios in which humans attempt to communicate with extraterrestrials. Sagan emphasized simplicity, universality, and clarity, advocating the use of mathematics and fundamental physical principles. Hawking warned of the unpredictability of contact, suggesting prudence and a focus on passive listening rather than active signaling. These perspectives underscore the balance between curiosity and caution in the quest to decode messages. Redundancy in signals may also aid decoding. If an alien civilization repeats information, employs multiple encoding layers, or provides self-correcting patterns, the recipient can cross-check interpretations. For example, a message might encode numbers alongside images, creating a double verification mechanism. This approach could drastically improve the chances of understanding, especially for civilizations with no shared linguistic or cultural context. Interdisciplinary collaboration is crucial. Decoding alien messages requires expertise from astrophysics, linguistics, computer science, cryptography, and cognitive science. Understanding potential alien intent involves speculation about psychology, sociology, and even philosophy. Teams of scientists working across disciplines maximize the probability of accurately interpreting signals, while also ensuring rigorous verification and error minimization. Simulations and test cases are used to prepare for actual alien signals. Researchers generate artificial messages with varying levels of complexity, ambiguity, and encoding techniques, challenging human and machine decoders. These exercises highlight potential pitfalls, reveal assumptions, and refine analytical methodologies. By practicing with synthetic messages, scientists develop strategies applicable to real, unexpected transmissions. The implications of successful decoding are profound. A confirmed and understandable message would transform human knowledge, culture, and worldview. Information about alien technology, biology, mathematics, or philosophy could accelerate scientific progress and inspire new approaches to global challenges. Socially, the knowledge that we are part of a larger intelligent community in the cosmos could reshape religion, ethics, and our conception of identity. In conclusion, decoding alien messages is one of the most intellectually and technologically demanding challenges humanity could face. It demands careful observation, sophisticated analysis, creativity, and patience. From detecting narrowband radio pulses to interpreting visual or temporal patterns, each step requires interdisciplinary expertise and meticulous methodology. While the challenges are immense, the potential rewards are equally staggering. The discovery that intelligent life exists beyond Earth, coupled with direct insight into a civilization that has evolved independently in the cosmos, the search is ongoing. Each passing year brings new observational technologies, advanced algorithms, and interstellar knowledge, bringing humanity ever closer to the possibility of receiving and understanding a message from the stars, whether through radio waves, laser pulses, or interstellar probes. The universe continues to whisper, and we continue to listen poised for the moment when the first intelligible alien message reaches our planet. The moment humanity receives a clear, intelligible signal from an extraterrestrial civilization, everything changes. Such a discovery would not only confirm that intelligent life exists beyond Earth, but also open an unprecedented window into alien knowledge, technology, and culture. What could we learn, and how might it transform our understanding of the universe? Science and physics would be the first frontier. A sufficiently advanced civilization might include in their message descriptions of physical laws, equations, or phenomena unknown to humanity. While we share a common universe, technological evolution can vary dramatically across species. Advanced knowledge of energy, generation, propulsion, quantum mechanics, or even new states of matter could revolutionize physics and engineering on Earth. For example, a message might explain methods for interstellar travel far beyond our current chemical rockets, providing insight into propulsion techniques like nuclear fusion antimatter drives, or manipulation of space-time itself. Astronomy and cosmology could also benefit. Alien civilizations may have mapped the universe in ways we cannot yet imagine, observing galaxies billions of light-years away, detecting dark matter structures, or interpreting cosmic microwave background anomalies with superior precision. They might share data about exoplanet climates, stellar life cycles, or the distribution of potentially habitable worlds across the Milky Way. This knowledge could help humanity refine models of cosmic evolution and better understand the origin and fate of the universe. Biology and medicine could undergo dramatic advances as well. Messages might include genetic blueprints, medical techniques, or strategies for extending lifespan and combating disease. By observing how life evolved under entirely different conditions, humans could gain comparative insights into genetics, physiology, and adaptation, even if not immediately applicable. Understanding alien biology would expand our conceptual framework for what life can be and how it thrives under varying planetary conditions. Technology and engineering are likely to be among the most transformative areas. An alien signal could reveal innovations in materials science, energy storage, or computational methods far beyond our current capabilities. For example, a civilization with millennia of experience might have mastered energy-efficient quantum computers, advanced AI architectures, or self-repairing materials. Even theoretical descriptions could inspire new experiments and technologies on Earth. Mathematics and logic could serve as the foundation of many lessons. A message might encode mathematical theorems, problem-solving frameworks, or logical constructs that are entirely novel to human minds. Exploring these concepts could expand the scope of abstract reasoning, providing new ways to model physical systems, optimize algorithms, or understand complex networks. The universality of mathematics would allow humans to recognize patterns even in entirely alien forms of logic, Cultural insights represent a fascinating frontier. While we cannot fully predict how alien civilizations communicate values, art, or philosophy, subtle cues might be embedded in their messages. Patterns in aesthetics, representations of concepts like time or morality, and symbolic structures could offer insight into alien cognition and societal priorities. Even abstract expressions, such as sequences representing music, rhythm, or visual composition, could convey aspects of culture that are not purely functional but deeply meaningful. Sociology and communication could also be inferred. The structure of the message itself fits clarity, redundancy, and complexity might indicate the civilization's methods of organization, education, and collaboration. A civilization capable of interstellar communication is likely to have sophisticated systems of governance, problem-solving, and knowledge transmission. By analyzing message structure, humans could infer aspects of alien social behavior, cooperation, and decision-making. Philosophical implications would be profound. Receiving an alien signal challenges anthropocentric assumptions about intelligence, morality, and our place in the cosmos. It raises questions about universal principles of ethics, the meaning of civilization, and the potential for shared understanding across species. Even the mere fact that another intelligence exists compels humanity to reconsider the uniqueness of our experience, prompting deep reflection on identity, purpose, and responsibility. Linguistic lessons are another avenue of discovery. Decoding an alien language of impartially would teach humans about alternative modes of thought and representation. It could reveal entirely new ways to encode meaning, from symbolic abstraction to mathematical grammar, expanding human linguistics and semiotics. The exercise of translation itself would foster cognitive flexibility and cross-disciplinary innovation. Global collaboration would become imperative. Unlike isolated discoveries, an alien signal affects all of humanity. Governments, scientists, and global institutions would need to coordinate decoding efforts, interpret the findings, and determine responsible communication strategies. This collective effort could foster unprecedented international collaboration, uniting humanity around a shared cosmic objective. The potential for indirect teaching is also significant. A message may include analogies, problem-solving exercises, or challenges designed to communicate complex ideas gradually. This approach mirrors human pedagogy, where understanding develops progressively. If extraterrestrial civilizations employ similar methods, they could effectively teach us advanced concepts without overwhelming us, allowing for stepwise comprehension and adoption of knowledge. Warning and risk assessment cannot be ignored. A signal may carry information that is either dangerous or misunderstood. For example, instructions for manipulating matter or energy without proper understanding could have catastrophic consequences. Decoding and applying alien knowledge responsibly requires rigorous safety protocols, multidisciplinary oversight, and careful risk assessment. The potential for misinterpretation underscores the importance of patience and humility in interacting with extraterrestrial intelligence. Long-term impacts on society would likely be transformative. Knowledge of alien existence and communication could reshape education, research priorities, technological development, and even geopolitical dynamics. Economies might pivot toward innovation inspired by extraterrestrial techniques. Philosophical and religious frameworks would evolve to incorporate the reality of non-human intelligence, potentially fostering new cultural paradigms centered on cosmic citizenship rather than terrestrial identity. Alone, psychological effects would be equally profound. For many individuals, the realization that intelligent life exists beyond Earth could evoke awe, a curiosity, and existential reflection. It might also trigger anxiety, uncertainty, or fear, particularly if the civilization appears technologically superior. Preparing societies for the reception of such signals is essential to ensure stability, informed discourse, and constructive engagement. Preparing for response involves both technical and ethical considerations. Scientists and policymakers would need to evaluate whether, when, and how humanity might reply to a received signal. Questions about tone, content, and potential consequences must be considered. Even a simple acknowledgement of receipt could have far-reaching effects, necessitating global consensus and careful deliberation. The role of imagination and speculation is invaluable. While actual signals may be rare or non-existent for decades or centuries, thinking about what we could learn helps shape current research, observational strategies, and theoretical models. Simulated signals, interstellar probe studies, and artificial message experiments allow humanity to prepare for eventual contact, maximizing our ability to decode, understand, and responsibly act upon any genuine communication. In conclusion, the knowledge embedded within a hypothetical alien signal spans science, technology, philosophy, culture, and ethics. From physics and engineering to linguistics and sociology, the lessons could redefine every aspect of human understanding. Even a fragment of intelligible information would be transformative, offering insights into cosmic evolution, the diversity of life, and the ingenuity of other civilizations. Ultimately, preparing to decode and interpret such messages is not merely an intellectual exercise, it is a practice in humility, patience, and curiosity. It underscores humanity's place in a vast, interconnected universe and reinforces the enduring importance of listening, learning, and contemplating what it truly means to be a conscious, communicative species in a galaxy teeming with possibility. Thank you for joining us on this incredible design. Only Ruby Kiss has the luxurious texture. That's the exuber texture that glides on /last and live long-lasting color. Communicative species and a cab, movie/may lest, medicinable, communicative, celeste. Journey through the cosmos. We've explored the mysteries of extraterrestrial life, interstellar visitors, and the signals that may one day reveal we are not alone. Whether you watch this video to learn, to wonder, or simply to drift off among the stars, your curiosity is what keeps our exploration alive. If you enjoyed this journey, don't forget to like, subscribe, and share your thoughts in the comments. What do you think? Have we already been noticed by other civilizations?